Welcome. In this course, I'm going to be talking about theoretical foundations of large-scale distributed systems. So these are the kinds of systems that you've all used. So these systems have to manage a lot of data, and one way in which they achieve their scale is by replicating and partitioning this data across multiple nodes. This can take several forms. First, you may have multiple data centers located across the world. So one point here is to tolerate disasters. So if one of these data centers goes down, that my data survives. And another one is minimizing latency. So for example, it's much faster for a user in Europe to access a data center in Europe than to go all the way to the US. Then within each of these data centers, the data would be spread across thousands of machines. This is partly for load balancing and also for fault tolerance, because these machines fail all the time. And finally, users may have replicas of data on their mobile devices to support offline use. Okay, so now ideally, programmers using such systems would like to have an illusion that all this replication is transparent. So they would want the system to provide what's called strong consistency model, meaning that the system behaves as though it processes requests serially on a centralized database. And you may have heard about words like linearizability or serializability, which are particular formalizations of this notion. This is expensive because it requires synchronization. So if I make an update in one place, I'll have to contact other replicas to make sure that they're aware of this update. And so this increases latency, and in some cases is plain impossible. So there is something called a cap theorem, which I'm going to prove later in this course, that says that you can't get all of three: strong consistency, immediate availability to answer user requests, and tolerance to network partitionings. And intuitively, this is because if you have a network partitioning, so say a cable across the Atlantic gets cut, and now I'm doing an update, then I either have to wait until the connection is repaired, so I lose availability, or I have to reply immediately, but then I can't synchronize with other replicas, so I lose consistency. And so because of this trade-off, there's been a lot of push in recent years to look at alternative architectures for these kinds of systems that relax synchronization between replicas and essentially give up strong consistency. So they provide some weak consistency criteria. So the way these systems operate is if you do an update at one replica, so for example, I update my bank account to deposit 100 euros, then I'll get an acknowledgement immediately, and then the effects of this update are going to be propagated to other replicas only later in the background. And so the good news is that this brings better scalability and availability. The bad news is that it weakens the consistency somewhat. So for example, this deposit may be seen by another user with a delay. Okay, and by far the most common application of these kinds of techniques that you must have all used is collaborative editing. If you're using a system like Google Docs or Office Online, then when you type a character into the system will acknowledge your update and display it before communicating with Google servers and with other clients. And this is really necessary in this case because it's unacceptable to wait for this update to reach other replicas. Just the latency of editing would be too high. And so nowadays there's a new generation of data stores that provide these kinds of architectures, so high scalability and low latency, but somewhat weaker consistency. And so, okay, so they don't provide strong consistency, so what kind of consistency do they provide? So when about 15 years ago there was so things like that appeared, there's been a lot of confusion. So for example, you need to be a bit careful when you design such systems because you can expose all kinds of anomalies to the users. So for example, here is one. So let's say we're in the context of something like a social network. So there is this user who first modifies the access object to remove her boss from the access list, and then posts a photo that she would like her boss not to see. And now, if this update so these updates are acknowledged immediately, and then they get delivered to other replicas asynchronously. Now, it may be the case that the first update is going to get to another replica later than the second update. And so in this case, when the user at another replica first reads the post, it will see the photo, but then it reads the access object, it will see all the default value rather than the modification that the user did that removed the boss. And so this is kind of an undesirable situation. So the weird thing here is that there is a what's called a causal dependency. So this right of photo is causally dependent on the right of no boss. So it happened after it, and so ideally we want the system to preserve this causal dependency, and in this case it doesn't do this. And so in this course, I'm going to be talking about consistency models which describe what kind of anomalies like this are allowed by your system, whether, for example, this particular behavior is allowed or not. And for example, there is something called causal consistency model that I'm going to define later that disallows this particular anomaly. Okay, so in the early days when these kinds of systems came along, there was quite a lot of confusion and misunderstanding. So there were quite poor guidelines on how to use data stores with such architectures, because they somewhat weaken consistency guarantees, but do they weaken them too much, too little, or is it okay for the application? And even the very notion of this, of the kinds of guarantees that they provide wasn't very well defined. So it was a very hype-type area, so you would have our survey articles and communications of the ACM, for example, by the CTO of Amazon, that would define the consistency criteria that these systems provide as eventual consistency. And if you look at the definition, it says something like this. So if no new updates are made to the database, then replicas will eventually reach a consistent state. And so there are some problems with this definition because first it assumes that kind of a false assumption that users stop shopping on Amazon, which never happens. And then second, it gives you a guarantee that the replicas will converge to the same state, but it doesn't quite tell you what the state is going to be. So that's kind of unsatisfactory. And so after these kinds of things, there's been a bit of a backlash in industry where the same companies that at first said that synchronization must be avoided like a plague and we should go for eventual consistency, switched to saying that designing applications to cope with anomalies is error-prone, time-consuming, and ultimately not worth the performance gains. So there was quite a debate in the area. And as usual, the truth is somewhere in the middle. The payoff from relaxing synchronization and weakening consistency is often worth it. It gives you high scalability, lower latency in geo-distribution, and it supports offline access. And in fact, nowadays, both strong and weak systems are used in industry. But using these kinds of systems is non-trivial, so programmers need help in using it. So they need some kind of programming abstractions that would make their life easier when programming weakly consistent systems. And they need some methods that would help them figure out whether weakening consistency affects the correctness of the application. And so this is what I'm going to be talking about in this course. And just to put this a bit into context, I've presented this whole thing as kind of a new development, but actually these kinds of issues have been with us for a very long time. Even the centralized SQL databases, like usual names like Oracle or SQL Server, they actually don't provide strong consistency either by default or at all, and this is to exploit the single node concurrency. And this is not a new development. They've been doing this since 1975, which is when the first relational database came along. So for quite a while. And there is finally another area where these kinds of issues are important, which is shared memory models. So nowadays, both multi-core processors and programming languages that compile onto them, they don't give you strong consistency because of processor compiler optimizations, and so you have to cope with these issues there as well. And so what I'm going to be talking about this course is some programming abstractions for weak consistency that let you program in an easier way, methods for specification of our consistency models that systems provide, and finally here's where a bit of a verification angle will come in. We're going to be talking about some methods and tools for reasoning about application correctness and the deeds about consistency. Okay, so let's start with the first part. So at first, I'm going to be talking about strong consistency and this CAP theorem that I mentioned before. So let me get a bit more formal. Since this is a lecture, I'm going to put some Greek symbols onto slides. I'm going to be assuming a database that manages a set of objects, so X, Y, Z, for example, and these objects are associated with types, things like integer, register, or list. And for each type, tau, I'm going to assume a set of operations. So for simplicity, I assume that these operations include arguments and return values that these operations return. So here's an example. So for example, I can have an integer register where the set of operations is either, I can either read the contents of a register or write an integer value to it, k. And the return values are either an integer, which is what I get out of a read, or just a dummy OK value, which is what I get for a write, that the write has been successfully performed. And another data type is counter, so it also has a read operation and an addition that adds k to the contents of the counter. So in this case, k is a natural, and the return values again are either a natural number, which is the response of a read, or an OK value. Okay, so now I'll need to define some kind of a semantics for these operations, and I'll start with a sequential semantics. So this is the semantics in an ordinary programming language. So for each type, tau, I'll assume a set of states, state tau. So these are the set of states in which this object may be in. There is an initial state sigma 0. And so, for example, the set of states for an integer register is the set of all integers, and for a counter is the set of all naturals. And now the semantics of an operation is going to be given by two functions. There is one function, op double bracket val. So given the state of this object, it gives the return value of this operation op, if it's performed in this state. And then another function is op double bracket state. So it tells you how an operation modifies the state of an object. So it takes the state the object was in before an operation and returns the state after applying the operation. So here's an example. For example, let's take the register. So as I said before, the set of states in this case is the set of integers. And then the function modifying the state of a register. So if I have an operation that writes k, then I apply it to some state sigma. The state sigma is essentially discarded and overwritten by the value that I'm writing. So I'm going to get k here. And then if I take the return value, then the return value is always okay because, well, the write always succeeds. And then the read function, the state function for it just doesn't change the state. So if I apply it in the state sigma, I'm going to get the same state because it's just a read. And the val function that determines the return value, given a state sigma, it just returns the state of the counter. So this is kind of a very simple definition. And then I can do the similar definition for counters. So in this case, if I want to add k to a counter in the state sigma, then the resulting state is going to be just sigma plus k, and the return value is going to be okay. And if I want to read the contents of the counter, then this doesn't change the state, so it's still sigma, and the value function, so the function determining the return value of the read, it just returns the state sigma. Okay, and then here just two notions that I'm going to need for the future. So some operations are read-only, so they don't modify the state. So for example, this read operation over here. So that's what I'm going to call them in this case. So you have op double bracket state sigma equals sigma. And the other operations are update operations. So they actually modify the state. This is when you don't have such an equality. Okay, now let's think about how you would specify consistency of a database managing these kinds of objects. So the database may have like a very complex implementation. So you may have some replicas that communicate using messengers. Maybe these replicas are located in different parts of the world. But when I'm using this system, I don't really care about the internals of the implementation. So all I care about is if I interact with it as a client by submitting some requests and getting responses, what kind of responses can I get? And so what I'm going to do is I'm going to introduce a notion of a history, which is a formal object that records the interactions between the clients and the system in a single execution. So for simplicity, I'm going to assume that every request yields a response. So a client submits requests like this. You have request, response, and the client never submits another request until the previous one has finished. So really you have this nice alternating sequence. Then if you take the pair of a request and a response, I can represent it by an event E. So I'm going to denote it like this. So it has several components. It has the object that I'm accessing, say X, the operation I'm performing, say write 42, and the return value I'm getting, say OK. Now, this total order in which a user submits requests, database people like to call it a session. So if you're in the shared memory programming languages, you would use a process or thread. And so you can just take the order on events in which the user submits them to the system, and this order I'm going to call it a session order. And this is a union of total per client orders. So for each client, you have a total order ordering the events that this client issued. And as a reminder, a total order is a transitive and irreflexive relation that orders any pair of elements one way or another. And so now the history is going to be a pair of a set of events and the session order. So what kind of operations I did and in what order. And a consistency model is a set of histories, calligraphic age. So it's a set of allowed database behavior. So this definition doesn't talk about the internals of the database. I'm just describing what kind of operations I did, given the set of events and their order in which I did them. Okay, and I can visualize histories kind of like this, where I have these events one after the other, and they're ordered by the session order, so in the order in which clients submitted them. And so here, these two orders are basically correspond to operations that the two clients did. Okay, now, so how do I define a consistency model? So this is what I want. So given my database, I want to define the set of histories that it produces. There are two ways of doing it, operational and axiomatic. So in the operational way, I essentially define this model by an idealized implementation. So I'm going to give a particular implementation of a database that's going to be more abstract than a real implementation, so somewhat easier to reason about, and the set of all behaviors it produces, that's my consistency specification. And then there is another way that's a bit more declarative that's called axiomatic, and I'm going to be talking about it a bit later. So let me explain what this operational specification is. So let me define it for the strong consistency model. It's going to be kind of trivial, but it will illustrate the issues that arise here, how you do these kinds of definitions. So if I want to define strong consistency operationally, then intuitively it's the strong consistency. I said it's kind of like an illusion that you have a single copy of your data. So I can say, well, my idealized implementation is going to have just a single server with a single copy of all objects. For example, I have some object X in some state sigma, and initially the state is 0. And then clients, they send requests to the server. Say this client wants to write 42 into this object X. And the server processes all these requests sequentially, so one after the other. So it will say, okay, now I'm going to write 42. So my state of this object is going to be 42, and reply to the client. And then if another client now comes along and wants to read the value of this object, then her request is going to be ordered after this write. So she's going to get 42 as a result. And so that's pretty much it. So that's very simple. And now the consistency model is going to be the set of all histories H that are produced by some execution of this abstract implementation. So that's the whole definition. And what I've defined just now is called sequential consistency. So it's one particular form of strong consistency. It's somewhat weaker than some other notions you may have heard about, such as linearizability, because they take into account real-time order of operations. But these ones I'm not going to be talking about. So for me, in this course, strong consistency is going to be sequential consistency. Okay, so the good thing about operational specifications is that they let one understand the intuitions behind implementations, but the bad thing is that they may become unwieldy for a weaker consistency models. So the implementation I showed you is kind of trivial, but for more complex models, they may become quite hairy. And they also sometimes overspecify behavior because you're giving an implementation, so there is always a danger that you're going to make some decisions that you didn't actually have to make. And so the way out of this is to use another style, which is called Axiomatic Specification. So the approach here is that I'm going to choose a set of relations over events, R1 to Rn. And the idea is that these events abstractly specify how operations are processed inside the database. Now, I'm going to consider another kind of object. So I used to have a history. Now I'm going to have what's called an abstract execution. So it's a pair of a history and a bunch of these relations saying how the events in this history were processed. And so if you unpack it, it's a tuple of the event set, the session order, so the order in which clients submitted the requests, and these relations saying how the database processed them. Then I'm going to choose a set of axioms, calligraphic A, that constrain abstract executions, so that kind of specify how the properties that the database ensures about event processing. And then a consistency model is going to be defined as the set of histories for which I can pick some relations, R1 to Rn, such that this abstract execution will satisfy my axioms, calligraphic A. So it's instructive to compare this with the definition I gave before for the operational specifications. So their consistency model was defined as the set of histories for which there exists an execution with this history that is produced by my abstract implementation. And so what happens is here in the axiomatic definition, I'm quantifying over these relations, R1 to Rn, kind of declaratively describing how the events are processed. And here I'm quantifying over a particular execution of my abstract implementation. So here I need to pick some relations. Here I need to pick a particular execution of the abstract implementation. And then in the axiomatic definition, these relations have to satisfy the axioms, and in the operational definitions, they have to be produced by this particular abstract implementation. So the axioms are kind of replace the abstract implementation in this case. So let me give you an example, which should make things a bit clearer. So again, I'm going to define sequential consistency in this axiomatic way. So I need to pick some relations, and to describe the processing the database does. And as I said, the main feature of sequential consistency is that it kind of can be explained by some total order in which the server processes requests. And so given this, of course, I'm going to pick just one relation to describe this processing, so TO for total order. That's just the total order on all events in the history that says in which order the server processes them. And so now my abstract execution is going to be a triple of the set of events, the session order that says in the order in which the clients submitted these requests, and the total order on request, which is the order in which the server processed them. And now sequential consistency is going to be the set of all histories, set of event session order, for which I can pick some total order, TO, such that the resulting abstract execution is going to satisfy some axioms. And the axioms are as follows. So there are two. The first one is very simple. It just says that session order has to be included into the total order. And that's because the server obviously processes requests in the order that the clients submit them. So this order in which this total order on requests describing server processing has to be consistent with the session order. And then the second condition is, so it's a bit of a mouthful to write it on the slide, but it's actually quite simple. I think Piotr wants to ask a question.
Yeah, there is maybe a quick question, just to make sure that we're on the same page. So could you come back to the notion of relation? So what exactly you mean by a relation?
It's a relation on the set capital E.
Yeah. So what? Yeah, whenever you define your correctness in an axiomatic way, you said that you need to relate the history to the abstract execution. So what this relation means?
No, so I need to define the notion of an abstract execution, and for that I just say, well, I have some relation, right? Like here in the case of our sequential consistency, I say my abstract execution is going to be a history and the total order on the events in this history. And then I just pick some axioms that constrain this relation. So this relation is in the end existentially quantified over here. So, Peter, does that clarify things or no? Not.
So this is basically it's kind of it's binary relation between two sets.
Oh, it's binary relation. Sorry, I should have.
That's what. Yeah. I think that,
okay. Sorry. Yes, it's a binary relation. Yeah.
Okay. Thanks.
Okay, so so as I said, you define, for example, sequential consistency as the set of histories for which there exists this total order on the set E, so binary relation that satisfies the axioms. And the first axiom just says that the session order is included into the total order. And the second axiom, what it says is how the return values of our operations are computed. And the way you compute them is you take all the, so if I'm doing an operation on a particular object, then what I can do is I can take all the operations on this object preceding it in this relation TO, apply them according to the sequential semantics that I gave before. So these are the state function, and then get a result using the value function. And so, for example, for integer registers, if I have an object of this particular type, then a read is gonna, what this axiom says is that a read returns the value that's written by the last preceding write in this total order TO, or 0 if there are no such writes. And so, for example, if I have my total order that says I first write 0 to x, then I write 42 to x, and now when I read from x, then I'm gonna have to return 42. So that's kind of the expected sequential semantics of the system. Okay, and now, as I said before, the sequential consistency is going to be the set of all histories, ESO, for which I can pick a total order TO that satisfies these kinds of conditions. Okay, and so now we can take some example of a history, for example, the one I showed to you before, and check if it's sequentially consistent. And I'm not going to bore you with details, but for this, I would need to pick some order in which our events are processed such that the return values are going to be consistent with this order. So the order is the one shown on the slide. And for example, the reason why I read 2 from Z here is because there is an earlier write of 2 to Z in this total order. So that's why this kind of execution satisfies the sequential consistency axioms. Okay, so there are these two styles, operational versus axiomatics. In this particular case that I showed you for sequential consistency, there isn't a lot of difference between them. So when I defined axiomatic semantics, I got rid of some things like messages between clients and the server, but I really didn't go that far from an operational specification. And but usually there is more of a difference for weaker models because I can specify pretty complex processing with these kinds of axioms. And so I'm going to show some things like that later in the course. Okay, so now here is one example that's going to be important for the proof of the CAP theorem. It's called the Decker example because it's a fragment of a Decker mutual exclusion algorithm. So let's take this program that uses a database managing objects X and Y. And there are 2 clients, so 2 sessions, A and B. And essentially what they're trying to do is solve some kind of mutual exclusion. So what the process A does, it writes 1 to X, and then the process B writes 1 to Y, and then they check the other guy's right. So this process checks, did I get there first? So I wrote 1 to X, is Y still 0? If it is, then I say that I'm gonna win, get access to resource or something. And this process does the reverse, writes 1 to Y, then reads from X, and if it reads 0, then it says I win. And so the claim here is that if I take all possible executions of this program over a sequentially consistent database, then there could be at most one winner. So let's show this. So assume the contrary, so we have two winners. That means we need to show that the following history is sequentially consistent, where I write 1 to X, and then read 0 from Y. That's what process A does. And then process B writes 1 to Y and reads 0 from X. And the SO edges, remember, they just denote the order in which clients do these requests. So because this is how these writes and reads are in this program, in this order, that's how they are in the history. And so now to show that this history is sequentially consistent, so I'm going to do this using this axiomatic specification. So I need to pick some total order TO on these requests that's going to be consistent with the session order, and the return values also have to be consistent with it. Okay, so let's see. So session order and TO have to be consistent, so that means that these edges have to be included into the total order. And then we have to also, so total order is total, right? So it has to relate any two events one way or another. So for example, let's consider these events. So you have the read from Y by this process and the write to Y by this process. So I have to relate them one way or another, and the return values have to be consistent with this order. Now, this read misses this write, so it reads 0. That means it can't come after this write in the total order, because then it would have to read 1. And so that means that our TO edge have to go this way. So that comes from the axiom about how return values are computed that I showed to you before. And then similarly, I can also look at this pair of events, which is kind of the same but symmetric. So I have read of 0 from X here and write of 1 to X. So again, the read has to come before the write, because otherwise it would have seen the write. And so I have to draw the TO edge like this. And so now I got a cycle in this order, and that's bad because the total order has to be irreflexive. So here you have all the edges implied by transitivity, so you can't have cycles. And so that's a contradiction. So that means that I cannot have two winners in this program, only one. Okay, and so now I'm going to use this example to actually prove this CAP theorem that I showed to you before. So first, let me state it a bit more precisely. So remember, the theorem says that no system, so the terms and conditions are with at least two processes. So if there was at least just one, it would be too simple. So at least two processes. So no system like this can implement a read-write register with strong consistency, availability, and partition tolerance. And so in this case, just to explain what the terms mean, so strong consistency, as everywhere in this course, means sequential consistency. Availability means that all operations eventually complete, so they can't hang. And partition tolerance means that the system continues to function even if I have permanent network partitionings. So processes in different partitions that they can't communicate in any way at all. Okay, so that's what I have to prove. Now let me try to sketch the proof. So it's going to be by contradiction. So we're going to assume that a system like this actually exists. So I can implement a database that provides these kinds of properties. And I'm going to run some experiments with this database using variants of this Decker program that I showed to you before. So in this case, I assume there is a database that allows access to these objects X and Y. And I'm going to take this particular type of a client that executes this program and see how it executes. And in all these executions, since we're talking about partition tolerance here, in all these executions, there's going to be a permanent network partitioning between these two processes, A and B. Okay, so here's the first experiment that I'm going to run. So the process A, it's going to execute the program as in the Decker example, so all these reads and writes. And the process B is gonna do nothing, so the client does not execute any kind of requests. And there is, of course, the database implementation that can be run at these two nodes, but these database implementations in different places that can't communicate because there is a network partitioning. So I'm going to denote this with this black bar. And so now let's see what kind of a behavior I can get here. So I assume that the database provides availability. So that means process A will eventually complete all its operations. These operations can't hang. And so you're going to get some kind of a finite execution XA of process A. Now, what kind of responses do I get? Well, this database has to be sequentially consistent. So this process, it writes 1 to X, reads Y, but there are no other reads or writes to Y, so no other operations on Y because process B doesn't do anything. And so that means this process has to, this process has to win, right? Because it's going to read 0 from Y. And so I get some kind of a finite execution of just this process where this process wins. Now I'm going to do a symmetric experiment. So the process B is going to execute the code in the Decker example. So the same kind of code, but symmetric, writing to Y and reading X. And process A is going to do nothing. And there is a network partitioning between them. So whatever messages the database implementation may be sending between them, they don't get through. So again, the database is always available. So even under this network partitioning, so all these operations by process B will have to complete. So I'm going to get a finite execution XB. And again, in this case, process B is going to win because it reads X. And there are no other operations on X in the system. And so sequential consistency says that it has to read 0. And so now I get these two finite executions where in one process A wins and in the other process B wins. And in both of these executions they're essentially executions of just one node. And this node cannot communicate with its environment in any way because I have a network partitioning. So now what this lets me do is to just stitch these two executions together. So I can consider an execution where first the node at which process A executes all the operations in the execution XA, and then the node at which the process B executes executes all operations in the execution XB. And now this whole execution is a valid execution of this Decker program where there is a permanent network partitioning between these two processes. So because before in these executions XA, XB, you had execution of a single process that couldn't communicate with its environment in any way. Well, now they do the same, but both of them execute independently of each other. And now that's a contradiction because this execution is an execution of a Decker program where both processes win, and that violates sequential consistency, and so this can't happen. And so in this way, I prove that I can't, in this case, get partition tolerance, sequential consistency, and immediate availability. And so the informal takeaway from this is that processes have to talk to each other, synchronize if you want to provide strong consistency. Okay, so this concludes the fragment about strong consistency. I don't know if there are any. So everybody can ask questions, I think, in the chat, and then periodically, I'm going to make a pause like this, and if there are questions, then tell me, and I can answer them. Guess there aren't, or
I think we are good for now. I think it's more or less.
Okay.
Yeah.
Okay, fine. So then I'll continue. Okay, so I can't provide strong consistency if I want to satisfy some nice properties. So what do? I weaken consistency. And so in the next fragment, next segment, I'm going to talk about what this mysterious eventually consistency means. And also I'm going to talk about one programming abstraction that makes it a bit easier to program over it, which is replicated data types. And in the course, I'm going to define all these things, both operationally and axiomatically, but first I'll start with operational definition because this makes it essentially obvious how implementations work. Okay, so let me define a bit the kind of systems I'm going to be talking about. So you have a database system that consists of multiple replicas, and all these replicas, they store the copy of all objects managed by the database. And so if you have two objects like X and Y, then they will live at the same time at all these replicas. And the replicas may be either a data center or a single machine or just your mobile phone. Now, for simplicity, I'm going to assume that replicas are reliable. So I assume they don't crash. I'm going to have enough problems because of network communication. And these replicas, they communicate via channels. So one replica can send a message to another. These channels are asynchronous, so there is no bound on how quickly a message will be delivered, in particular because you may have network partitioning. But it's going to be convenient for me to assume that these channels are also reliable. So every message is eventually delivered, essentially because every partition eventually heals. So if there is a partition, I can wait for long enough time, and it will repair itself. So I want to talk about systems that provide immediate availability, even despite network partitionings. And so people usually use the term high availability to describe this property. So the idea here is that clients connect to a replica of their choice. For example, these clients go to these replicas, do the operations they want, for example, these two writes. And then the replicas, they have to respond to operations immediately without any communication. And then they will propagate effects to other replicas later in the background. So that means that even if I have network partitioning, so I cannot communicate with other replicas, I can still immediately reply to the client. And so this kind of system is always available, has low latency, but it may not be strongly consistent. Okay, now I will want the system to provide, at the very least, this weak notion of eventual consistency that I showed to you before. So if no new updates are made to the database, then replicas will eventually converge to the same state. Actually, this kind of a condition is not something new. This is something that distributed computing theory people called quiescent consistency for a very long time. So this is quite a weak notion, and later I'm going to define a bit more stronger and precise formulations of eventual consistency. Okay, now I have these objects living in multiple places at the same time, so I'm going to have to introduce a new kind of data type for these objects, which is called replicated data type. It's also called CRDTs, where people can't quite agree on what the letter C stands, like commutative, convergent, or conflict-free. So I'm just going to call them replicated data types. And I'm going to show you now an operational specifications, which is pretty close to how these replicated data types are actually implemented. But just as a disclaimer, there are different ways of implementing them. So here I'm going to be talking about just one way, which is called operation-based, but there are others. And so now I'm going to assume this database where every object is associated with a type. And this type, as before, gives me an operation signature, so what kind of operations I can perform. And so for now, I'll just fix one object with a single type. Okay, now let me recap briefly the sequential semantics that I defined before, because I'm going to use pretty much the same notation. So before, when I had an object that was strongly consistent, so lived in one place, I had a set of states that this object can be in, the initial state, and then I had these two functions. One function that, given the state of the object, returns the return value of an operation op that I perform on it, and then the other function that tells me how an operation modifies the state of an object. So given a state, it returns the state after applying the operation. And so now I want to do the same kind of thing with these replicated data types. So in this case, I'm going to have, again, the set of states. So sigma is 1. And in this case, these states, they represent the state of an object at one replica. So not in the whole system. So the object lives in multiple places at the same time. But if I take one replica, then the state is a set of states at this replica. And now, if I do an operation at this replica, so remember, these are highly available systems. So I come to one replica, do an operation, and immediately get a response without communication with others. So in this case, I can determine how the return value of this operation is computed based on just the state of this replica. And so I can do this exactly in the same way as I did with the sequential data types. So given an operation, I'm going to define this function double bracket val that says, if you know the state of this object at this replica, then here is the return value. So that's simple. And now where it's going to get more complex is with how the operation modifies the state of an object. And that's because okay, so there's a question or something. Actually, somebody asked if, do you understand correctly that cap theorem still holds when we consider not permanent but arbitrary long partitions? Yeah, well, yes, but then you also have, if you strengthen the availability like I did here, which is you have to reply immediately without communication, so not eventually. But maybe let me next time next time somebody wants to. Anyway, people can ask questions during the next stop that I make. Okay, so I need to define how an operation changes the state of a replica. So the problem is that it changes the state not of just of the replica where it originally was executed, but also some target replica. Right, so when I do this operation at this replica, I'm going to send a message to another replica, say, hey, I did this operation. At some point, this replica is going to get this operation, and we'll have to apply it to its state. Now, the problem is that by that time, this replica may be in some other state, sigma prime, that's different from the state sigma that I used when I was applying this operation at the beginning. Right, and so I need to define how this operation is going to change the state sigma prime. Okay, so the way I'm going to do this is like this. So before I just had a function from state to state. Here I'm going to have a bit of a more complex function. So what it does is it takes a state sigma, so the state in which the operation was originally applied. And what it does is it returns another function, which we call an effector. And this is a function that is sent in a message to another replica. So what it does is it takes the state as its argument, the state of the object at the target replica, so the replica that receives this message, so sigma prime, and it tells me how it's going to change the state at this replica, so what the resulting state is going to be. So the resulting state of this replica is going to be this op double bracket f of sigma, so that's this argument, and then applied the resulting effector applied to sigma prime. Okay, so let me give you an example, then it's going to become clearer, I hope. So let's take the counter. So that's one of the data types I used before. So the set of states here is a set of naturals. So these are the states at one replica. So if you have a counter at one replica, then the state there is a natural. The state in the whole system is, of course, the set of the state of the counter at each replica. So it's kind of more complex. And now if I take the read function, so that's the most simple, the simplest thing, then the return value, if I apply it to state sigma, is going to be sigma. So I just read the state of the object at this replica where I'm executing this read. And then the double bracket f function returns an identity function because read doesn't modify the state. So here I'm using, this is the typical notation that programming languages people like to use. I'm going to denote functions using this lambda symbol, where the next symbol is the parameter, and then the rest is the function body. And so in this case, this is an identity function. And now let's look at the additions. So let's say I want to add 100 to the value of my counter. And I'm doing this at a replica where the state of the counter is sigma. In this case, I'm actually going to ignore the state sigma. What I'm going to return is a function that takes any state sigma prime, that is the state of the object at whatever replica this update gets to. And then this function is going to just return sigma prime plus 100. So it's going to take whatever state you had at a replica. So for example, let's say I do an addition of 100 here. This message gets here to this replica, and by that time, the value of the counter at this replica is 50. So then the value of the counter is going to be, in the end, 150. Okay, so now this definition is actually a bit more subtle than may seem at first sight, because I could easily screw it up. So I had the state sigma that I decided to ignore. Well, let's say one possible definition would be instead of returning a function that adds 100 to whatever state sigma prime you had when you got this message, you could instead take sigma, so the state of the counter at the origin replica, add 100, and take a function that just overrides the state of the counter with sigma plus 100. So in this case, I would get into trouble. So I would violate even the weakest notion of eventual consistency. So let's see why. So I'm going to go through this example. So let's say you have this counter living at 2 replicas, and initially it's 0. And then at one replica at 100, and at another replica at 200. Now, so these additions, they are initially executed at these replicas, and they generate effectors. So in this case, the effector is going to be a function that takes whatever state you had and overwrites it with 100, because 0 plus 100 is 100, so that's the new value that I'm sending. And here I'm going to get the same thing, that's 200. And these functions, they're used both to update the origin replicas where I originally did the operation, and other replicas that may receive this update. And so initially I will apply them at the origin replicas. So I'm going to get the values of the counter 100 and 200 here. And then later, these updates are going to get to the counterpart replica. And then this replica, okay, so it first applied its own update that wrote 100 into the counter, and then it applied the remote update that wrote 200, so that 200 overwrote 100. And then here is the reverse. I applied 200, and then later I overwrote it by 100. And so now I violated quiescent consistency because all the updates have been delivered, but replicas will never converge. So essentially I lost some of the updates. And so this is not something I want to happen. And for this reason, to ensure that quiescent consistency is actually going to hold, I need to require that effectors commute. So if I take any two operations, op1 and op2, executed in two states, sigma 1 and sigma 2, generate their effectors, so these are complicated expressions, and apply them in two different orders, the result always has to be the same. And that was the case for my original definition of the counter.
Yeah,
and so, yeah.
Yeah, so I'm sorry, just a quick question. First, one question for me. Could you remind what you mean exactly by effectors?
So effector is this, so effector is this function. So it's this part of the type of this thing. So if it's a function that you send to other replicas. If you want to add 100 to your counter, you send the function saying, please add 100. So this is this part of the type.
It maps a state to a state. Yeah. Okay.
Yeah, it's a state update. Yeah. So in this case, this is this function. So lambda sigma prime plus 100, and this double bracket f. So I had to pick some notation. This is a function that, given a state where you're doing an operation, it generates an effector.
Mm-hmm. And then there was a question on the channel, which I personally, I'm not sure I understand it, but I will just spell it out. Maybe you will understand it better.
Okay.
So people ask for a comment on the notion of overspecified behavior. And what kind of decision?
That was a long time ago, but okay, let me try to answer. It's just that you can, I mean, it's a general thing with specifications. If you define specification by an abstract implementation, so essentially specification needs to define a set of all possible implementations of this kind of a consistency model, and you can make different decisions in these implementations. Where you define a specification by an operational implementation, you can make some particular decision that will restrict our behaviors in an unintended way. So if you look at like programming languages, I don't know, like for example in C or something, that would say, oh, the order of evaluation of arguments is undefined. That's because they want the compiler to be able to make any decision. Now, if I now try to define the semantics by saying, oh, I give you a compiler that evaluates these arguments in this particular order, then this kind of an example of an overspecification.
Yeah, but is there any like criterion which you can say that the specification is
it's pure. No, it's pure. I mean, it's sort of subjective. Because whatever specification I do, it will still define a model. So I could say, well, this is my model. But sometimes you make these kinds of mistakes with implementations. Okay.
Thank you very much.
Okay, fine. So to ensure quiescent consistency, I need to require that effectors, so these functions determining updates, they commute. And if this is so, then I'm going to get this property of convergence that says that if two replicas receive the same set of updates, then they will end up in the same state, even if they receive updates in different orders. And that's because all the updates just commute. And this will imply this notion of quiescent consistency that I'm after, that if no new updates are made to the database, then replicas will eventually converge to the same state. And that's because if you stop making updates, then eventually all replicas will receive all the updates you've made so far, and they will, by convergence, they will get into the same state. And so there's actually a zoo of these replicated data types that people have developed. So I showed you a counter, which is just one example, but there are many others. So registers, sets, you name it. And so in the rest of the segment, I'm going to show you a couple of more implementations, just to give you a bit of a wider range of things that can be done. Okay, and so I showed you a counter, so the obvious next thing is to look at read-write registers. And here there's a bit of a problem because, let's say I have two users that are connected to different replicas, and one writes 1 to the register and another writes 2 to the register. And they're completely unaware of each other because these replicas so these operations, they have to complete without any communication with other replicas. And so now when after these operations are done and the replicas exchange updates, then we'll essentially have a conflict because there are these two operations that did contradictory things and they weren't aware of each other. And there is really no right or wrong way to resolve this conflict. It really depends on the application requirements. For example, one option would be to just report the conflict to the user, say, hey, there were like multiple updates, here are all of them, do something. There is actually a data type for that called multi-value register. Instead, I'm going to show you something a bit simpler that takes the intuition from shared memory models. So if you look at if this were a usual concurrent programming language where two threads did these kinds of writes, then essentially what would happen is one of these writes will win consistently. So there's going to be one outcome, either one wins or the other. And so you can achieve the same outcome in a distributed system by tagging these writes with timestamps and letting the last guy win. So the write with a higher timestamp will overwrite the write with a lower timestamp. And this is what's called the data type that works like this is what's called a last write to wins register. It's also going to be important because this is a link to the shared memory consistency models. Okay, so let me explain how this data type works. So there is let's say we have the set of states at one replica. In this case, the set of states is going to be the set of pairs of a value, which the register stores, and the timestamp of this value. And if I read a value, so I have to define this function double bracket val, then I'm going to just discard the timestamp part and return the value to the user. So the timestamp is something that's used by the implementation. The user doesn't have to see it. Now here's the write semantics, sort of complicated, but actually says something very simple. So again, I have to define this f function that, given a state in which this register, in which this update gets executed, it returns to me the effector, so how the states of other replicas are going to be updated. So let's say I'm going to write a value v new, and originally I had some value v. So now what I'm going to do is I'm going to generate a new unique timestamp for this particular update. So for example, in this execution, I may have the right of 1 get timestamp t1, right of 2 get timestamp t2, and maybe they would have to be totally ordered somehow. So let's say t1 is less than t2. And then I'm going to return an effector, which is this function that gets sent to other replicas and tells them how to update their state. And the effector is a function that takes the state at the recipient replica, so v prime, t prime. So let's say if I'm this replica, the second one sends right of 2 to the first replica, then let's say the state v prime t prime is the state of this replica. So then this effector tells me how I'm going to modify that state. And here I have an if then else that compares timestamps. So if the timestamp, the time sending, which is t new, is greater than the timestamp of the write at the destination replica t prime, then I will overwrite this, overwrite the its state with the new value. So I'm going to return v new t new. Otherwise, I'm going to leave the state as is. Oh, actually, this is a typo. It should be v prime t prime. Okay, and so here are. So remember, I assume that t1 is less than t2. So in this case, t2 wins over the timestamp t1 of this replica, and so the write of 2 is going to overwrite the write of 1 at this replica. And then symmetrically, here, the write of 1 has a timestamp t1. It's less than the timestamp t2 at this replica. And so when the second replica receives the update of the first replica, this update is going to get discarded and the state is going to be as is. And so in the end, I'm going to end up with 2 at both replicas, which is what I wanted to get the eventual consistency. And that's because the effectors that I generate here, so you can easily check that they actually commute. And that's because the write with the highest timestamp always wins, regardless of the order of application. Okay, so that's how the register works. Now I need to say how I'm generate timestamps. That's the only missing bit. So one option, which is very simple, is to use the wall clock time at the machine. So just look at the value of the clock and assign the timestamp using it. That's a bit suboptimal because it can lead to strange results when clocks are out of sync. So clocks at machines are never completely in sync. There is always some clock skew. And this may lead to problems. So let me illustrate how. Let's say you have this user who writes 1 with timestamp t1. Then it sends, so this replica propagates this update to some other replica, number 2. And this replica, there is another user who reads 1, so sees this update, and then says, oh, okay, I want to overwrite it with 2, so writes 2. And now let's imagine that all the timestamps are taken from one wall clock time. So here I'm going to have some timestamp t1, here I'm going to have some timestamp t2. Now, because of clock skew, it might actually happen that t1 is going to get a higher timestamp than t2. Because the clock at this machine of the first user was speeding up a bit. And so now this can lead to strange results because let's say both of these writes propagate to another replica of a third user. And in this case, this user will read 1 because the update, the first update by the first user is going to overwrite the second update. Right. And this is kind of weird because, again, I violated causality because really this write of 2 was meant to overwrite this write of 1. And so ideally, I want this things like that not to happen. And the solution is not to use wall clock time, but use logical clocks that have some prettier properties than your usual wall clocks. And so this notion of a logical clock is due to Lampard. So for this reason, they're called Lampard clocks. And this is a concept that's used quite a lot in distributed systems. So let me quickly explain what they are and how they're going to be applied in this example. Yeah.
Yeah, sorry. Before we go to the Lampard's clock, just to clarify, so you mentioned causality. Was causality one of the formal requirements you imposed on your system before? Because if you just think about eventual consistency.
No. So you're right. It's just that so a bit later, I'm gonna define a spectrum of models that are a bit stronger than eventual consistency. So kind of go between eventual and causal consistency, and this is gonna be important for implementing one of them. So that's why I generate these timestamps in this particular way. So later, I'm gonna show a bit more declarative definition where the soundness of the definition will depend on, or if you want to implement it, you'll have to do these kinds of things. But yeah, you're right. If I want to have like a vanilla or eventually consistent implementation, then I'm already done. I don't need to do anything else.
Yeah, so you can go with clock on the wall, even if
you can go. You can't get. Yeah. So really, when I said it's undesirable, formally speaking, I want a bit of a stronger consistency model.
Yeah, then the guy with the fastest clock always wins.
Well, no, it's not going to be a wall clock time. It's going to be consistent with. So it's going to be consistent with causality. I'm going to define more precisely what that means. There's going to be some notion of visibility of updates, and the way the conflicts are resolved has to be consistent with it. But yeah, that's the intention.
Okay, thanks.
Okay, so let me define these Lampard clocks. So the idea here is that instead of a wall clock time, replica is going to maintain a spatial counter that's incremented on each operation. So this counter is time, so initially it's 1, and then if I do an operation, then I assign a timestamp to this operation from this counter, and then I increment the counter. So if I do a write of 1, then it's going to get timestamp 1, and the counter is going to be incremented to 2. Then I'm going to do another write, so it's going to get timestamp 2, and the counter is going to be incremented further. And then I can do the same thing at another replica. So again, the time can be 1, and then if I do a write of 1, then it's going to get timestamp 1. Now, this doesn't quite work because I need timestamps to be unique. And here I generated 2 timestamps of 1 for 2 different writes, so that's bad. So to resolve this, I'm going to say that a timestamp is actually a pair of a counter value and a replica ID, where the replica IDs are used to break ties. So the way I'm going to compare timestamps is I'm going to compare these pairs by first comparing the counters. So if one counter is less than the other, then we're done. So this timestamp is less than the other timestamp. And if the counters are equal, then I'm going to compare replica identifiers. And so really, actually, in all these cases, the timestamps are going to be a pairs of the counter value and the replica, R1 here, R2 here. And so if R1 is less than R2, then I can actually compare this time here, 1 R1 with 1 R2, and the first is going to be less than the second. And so there is just one more rule about how these Lampard clocks are managed, which is important to disallow this previous example. And so let me show it by running through it again. So same situation. So let's say one user does write of 1, and the time at this replica is T1. So this is the timestamp I'm going to get, T1 and R1, and the time is going to be incremented. And then I'm going to send a message to another replica. So let's say that replica had time T2 when it receives this message. Then the important rule of these Lampard clocks is that when you receive a message from another replica that contains a timestamp, you bump up your clock above this timestamp that you receive. So in this case, the time after receiving this message has to be a maximum of T1 plus 1. So it's 1 above the timestamp T1 that I'm receiving, and T2, which is the time I had before. And so now if I do a read, I'm going to see, obviously, the update that I've just received. And now if I'm going to do a write, then this write is going to get a timestamp, well, assuming that T1 was greater than T2, which was my bet scenario before, it's going to get timestamp 1 above the highest timestamp, which is T1. So it's going to be T1 plus 1, and R2, the identifier of this replica. And now if another user receives both of these updates, then it's going to read the one with the highest timestamp. And now write of 2 is going to win because T1 plus 1 is greater than T1. It's going to win because of this rule that when I receive this right of 1, I bumped up my clock to be above it. Okay, so that's like so these are Lampard clocks, and now I can just plug them into my register to generate timestamp, and I'm gonna get a register with a bit prettier properties that don't lead to these kinds of issues that I showed before. And in a while, I'm going to show a bit of a declarative definition of what I've just done, so what kind of consistency model I've just defined. Okay, and before I conclude this segment, let me just I'll show you an example of one more data type, which is a replicated set, which is kind of interesting. Now, for the sake of an example, let's say the set represents a kind of a stupid shopping cart that contains at most one element of each item, right? So it's a set, it's not a multi-set. And so let's say we have this example where initially you have a book in your cart. You bought a book at Amazon, and then this guy wants to remove this book. So it kind of changed his mind. And then his wife, she's like really bossy, and she said, no, I actually want to add it again. So now, again, we have a conflict like we did with the registers, because these events are kind of contradictory, and the problem is that these two replicas that these two people are connected to have to reply to them immediately. So you somehow have to decide what you're going to do in this situation. And so in particular, what we need to decide is whether this remove is going to affect the concurrent add. So this removed for sure wanted to remove the book that was already in the cart, but what's going to happen with the concurrent operation? And so again, there is no right or wrong way to decide, depends on the application requirements. And there are different choices. You can, again, choose who wins based on operation timestamps, like in the case of last writer wins register. In this case, maybe not so intuitive because you probably want some consistent outcome. And there are two types of consistent outcomes. You can either say that remove is going to win. So remove is going to remove not only the occurrences of the element that were already in the set, but also all the concurrent additions, or the add is going to win. So the remove is going to have no effect over concurrent additions. And so depending on these choices, there are different types of set data types that you can design. So let me show you a add-win set, which is one of the choices. So in this case, in the case of this execution, it will actually give you an outcome that the book is still in the cart, because this remove will cancel the original addition, but not the concurrent addition that was done at the same time at a different replica. Okay, so now the subtlety of this data type is that remove acts differently on different additions depending on whether they are concurrent or not. And so for this reason, internally, even though this is just a set, internally, we're going to have to represent different additions separately when we talk about the contents of the set. And so the state of this set at each replica is going to be a set of pairs consisting of the element you're adding, like a book, and some unique identifier for this particular addition. So now let's see how this works. So each addition is going to create a new element, right? So for example, let's say like in my example, I had a state of a set where I had a book and it was added and the identifier was 1, and then I want to add the book again. Then the effector function for this addition, so if I want to add a value v, the effector function is going to return so there's going to be a function that takes the state of the set at the target replica that receives this update and adds the element v that I'm adding with some unique identifier. Okay, and so in this case, it's going to generate a function that adds book with some identifier, say 2. And so after the addition here, I'm going to have actually two books under the hood, book with 1 and book with 2. Now, if I read the contents of the set, then all these metadata gets ignored. So the IDs are just for the implementation, so I don't see them. If I want to read, so I want to define this function double bracket val over state sigma, then it's going to return the set of all values v, for which there is some pair of v with some identifier in the state of the set. So in this case, it's going to be just a book without any identifiers. Now, the most interesting part is the remove. So let's say at some other replica in my example. So here I also had a book, so edition number 1, and I want to remove the book. So the idea is that a remove has to, so it's Edwin set, so remove has to remove whatever it sees, but it should have no effect over concurrent additions. And so the way I'm going to achieve this is I'm going to say remove V is going to remove all the instances of the book that are currently present at this replica. So the effector function for remove of V is going to be a function that takes whatever state sigma prime that I'm applying this to, and removes from it all the elements with this value V that were in the state sigma where I originally applied this removal. Okay, so let me walk through the example, so this should be clear. So I'm doing remove of book at this replica. So what I'm going to do is I'm going to take all the instances of the book I see here, which is book number 1, and create a function that takes whatever state you have at some replica and removes only these instances. And so if I apply it at my replica, then of course I'm just going to remove whatever is there. So I'm going to end up with an empty set. But now if I send it to another replica, say this one, then I'm going to remove the instance number 1, but I'm going to remove whatever instances that are there that I didn't see when I was doing the remove. So book 2 is in the end going to be still in the replica. And now if I finally propagate this edition of book 2 to this replica, then here I had an empty set, but now I'm receiving a new edition, so I'm going to have a book 2. And so in the end, I get eventual consistency, so the replicas converge. And this is because of the effector, as I defined, it's commutative, so it only adds or removes fixed elements, so it doesn't really matter in what order you applied. Okay, so the takeaways are that you need to ensure commutativity to guarantee quiescent consistency, and really there is a space of choices you may do about how to resolve conflicts. And so I presented to you just a part of the zoo, but really there are more things than that. And there are now some databases that actually provide these data types as part of the APIs. So Redis, for example, is one of them. And more often programmers, they just implement something like this on their own without using a database. And so there is a bunch of companies that use these kinds of techniques. And as I said before, by far the most widespread application that you've all used is collaborative editing, so things like Google Docs. And at the core, what it is essentially a data type that is a list of formatted characters. So I presented to you counters and sets. So in this case, this is a list. So I didn't have time to talk about it because it's a bit of a more complicated object, but the techniques are pretty much the same. And so now to tie this all together, so I've presented you this kind of specification of data types. So now if I want to define eventual consistency in a bit of a more precise way, then if I'm given a database with a bunch of objects of various replicated data types, say Edwin sets, registers, etc., then I can define eventually consistent model as the set of all histories that are produced by any client interactions, assuming any way in which messages can be delivered. So I just take the set of all possible executions of this kind of abstract implementation, and I'm going to get eventual consistency. And this implies quiescent consistency because, as I said before, I assumed that effectors commute. Okay, that concludes the fragment about eventual consistency. So I don't know if there are any questions, and I can take them. Otherwise, I'll go on.
There was a question about effector for right. In the definition of the effector for right, other arguments V and T are used at all. Could T be used instead of T of nu? It seems about some.
Yeah. So here, okay. So first of all, remember there was a typo. So this is this is V prime T prime. The arguments here are not used at all, and that's because in this case the write that you do is meant to overwrite whatever was in the set before. So you just erase it anyway. So the arguments are not used. So that's intentional. And what was the second? So you said the part of the question, are they used? And then the second part was...
No, it's the same. Could T be used instead of T on U? Of T on U?
No, because the intention is that all timestamps are unique. Because for any two writes, I need to decide whether one overwrites the other. So I can't reuse timestamps.
Okay.
But it's usually not a problem to make them unique by just slapping replica identifiers to break ties.
I see. I haven't seen any questions here. Oh.
I have a quick question. So you have these two examples. One is about last writer wins scenario, and the other one about the shopping cart. So in the shopping cart case, so you have like you need to break the ties if you have add and removes, which are a priori conflicting operations, and you decide that, for example, the remove wins, or add wins. But does it matter if you have, for example, sequential executions? You have if you first add a book and then remove book, or a first remove book and then add book, then the result should be the same.
No, it shouldn't matter. So it shouldn't matter. So all these data types should behave the same in a sequential execution. But this matters only for conflicts when you do conflicting updates in different places.
So the notion of causality here is not important.
So actually, now that I'm realizing, I think the implementation I'll probably need to add an errata to when in the exercise sheet, because I think in the implementation for effectors to commute, you actually need to run this under causal delivery. But I'm gonna talk about this in the next segment anyway.
Okay. Well, I think we are done. There are no questions. I hope.
I'm sorry. There's one question more. More.
Yeah. Okay.
In the shopping cart example, the thread on the left adds an element into the set which is already present. Why is that allowed? I think that when there was two examples.
It's just maybe one thing is this is just maybe you shouldn't view it too much as a shopping cart. This was I just hacked a shopping cart notion for the example to give names to elements. But really it's just a set, and maybe so this user, for example, one option is this user may not even be aware of this addition. Maybe this addition, the original one, that cart is equal to book, that was done at some third replica, and when this user does her addition, she's not even aware of it. So I didn't draw this at the here, but it could be like that as well. So you can make multiple additions, and maybe this guy is aware of some of them, but not others.
I see. Now we all.
Okay. So actually, we have not much time, but let me just start the next segment, and then we'll see. Okay. So now
I'm sorry. Just more questions.
Yes.
Very interesting talk. Consider the distributed reference counter based on CDT PN counter. There are some heavy objects in distributed database that must be deleted in case if the PNC counter values turn to 0. May the physical deletion be implemented correctly in system with weak consistency? You can see it in Telegram. It's quite.
So PN counter is one more data type that I didn't talk about. It's kind of a data type that supports subtractions, not only additions. I'm kind of gonna talk about this a bit later, depending on what you mean by correctly. But with this counter, if you want it not to go below 0 ever, then this is tricky. And so later in the talk, if I'm ever going to get to that part, I'm going to talk about how to mix strong and weak consistency, so that you could actually say get a counter that never goes below 0, even with subtractions.
Thank you. So we have just 5 minutes.
Okay, so actually I do. Oh, that's okay. So I can, because I have some stuff here where I can start. Okay, so in the second part of the talk, I'll be talking a bit about our axiomatic specifications. So we're kind of gonna do the same thing axiomatically, so bit more declarative specifications. And here, when we had a discussion with Piotr earlier, I said that, well, really there is a spectrum of models. So I'm not gonna just be defining very vanilla eventual consistency. And so there is really a spectrum of models that allow or disallow various anomalies, and these axiomatic definitions are very good to define them. So let me just illustrate the kinds of things that happen here. So, for example, one anomaly is the following. Let's say I add 1 to the counter, and then the same user reads this counter again. So if you take really vanilla eventual consistency, it may be the case that these two requests are going to go to different replicas. So the first adds 1, but the second will connect to another replica and will not see the update performed by the first operation. So that's kind of bad, and it could be disallowed if the client just sticks to the same replica, for example. And this is something that's called read your rights guarantee. So this is something that you would ideally want to have in your system. And then here's another example, which is a variation on my previous example with causal consistency. So here again we have this user who writes a no boss into the access field, and then writes a photo into the post. And then here I also, to make things clear, I also wrote also displayed the initial write of all to the access. And so now it may be the case that these updates, they're propagated completely asynchronously. So it might happen that the first and the third update, they will get to some replica earlier than the second update. And so in this case, I'm going to have this undesirable situation where the boss can see the photo, but sees only the default access permissions that are all. And so here, the weird thing is that there is a causality chain from this write of no boss to the read of access over here, because there is a sequence of either client operations or message delivery edges. And ideally, I would want to preserve this causality when I expose operations to users. And so these kinds of anomaly, which is causal consistency, is disallowed. Causality violation is disallowed by another model, which is called causal consistency. And so really, there is quite a lot of replicated data type implementations. So I showed you multiple replicated data types, and then each one of them can be replicated in different ways. So for example, you can send snapshots of state instead of operations. There are different message delivery guarantees. So do you preserve causality or not? And so ideally, you want specifications that abstract from these from the details of how all these things are implemented and specify them a bit more declaratively. And in this, like in the rest of the course, I'm going to be talking about axiomatic specifications that allow you to achieve this. Okay, I think this is maybe a good, we just have 2 minutes left, so maybe it's a good time to stop, and then I'll continue in the rest of the course.
Okay.
So maybe if you can take a couple of questions. I don't know if there are questions.
Sure, if there are, yeah.
Yeah. So one question is about quiescent consistency, which you mentioned at the beginning. So if I understand correctly, it's just a weak form of eventual consistency, or one of the variants of it.
Well, I think the way people defined eventual consistency like early in the days, it kind of corresponds to quiescent consistency. They just didn't call it like this. But really, when the systems provide something a bit stronger, which is the kind of specifications that I showed before. So they were kind of operational. I'm going to show some axiomatic ones that, for example, allow you to determine a bit, at least something about the message, or like what kind of, about the return values given, say, message deliveries and things like that.
I see. And there's actually a great suggestion. If you could just sort of recap the spectrum of consistency criteria we mentioned, like strong, sequential, weak.
Well, I have some slides about this. later, so I can just bring it up maybe. But it's at the very end. Not sure I'm gonna probably not gonna cover all of this.
Of course,
So
just to get a rough idea of what's going on.
So this is it's actually a subset of the consistency zoo. So there is this eventual consistency, which is, I don't know, maybe quiescent consistency is even weaker. So quiescent consistency is this small property that if you do finitely many updates, then eventually you will see the same thing at all replicas.
I'm sorry, just remind, we have few seconds
seconds left. Okay,
to finish our first part.
I can continue.
Okay, it would be nice if we continue at 12 o'clock I'm sorry, at 12 and then half of an hour. Thank you very much, and I hope you could continue this discussion later. Thank you.
Okay, thank you.
Okay, well, thanks a lot.
So there were some questions about how in the chat about how quiescent consistency relates to CRDTs. It's a bit of an apples and oranges thing. So if I have a database, I have to say what kind of data types it has, right? So these are like objects of what. It can be CRDTs, it can be something else. You can just do a usual read-write register with usual writes without any timestamps, and I can still state a consistency condition, such as quiescent consistency. So it's kind of orthogonal. And then I can have a database using CRDTs that gives you these kinds of properties like quiescent consistency. So to recap, there was I'm going to be talking a bit more about this, but there is a bit of a consistency zoo with different conditions. And so there is eventual consistency or quiescent consistency. So eventual consistency, the way I define it, is a bit more precise. Quiescent consistency, it's this notion I introduced before that gives guarantees only under finitely many updates. Then there are session guarantees, so these are things like read your writes, the fact that they give some guarantees that ensure that clients have a monotonic view of the state of the database. Then there is causal consistency, and then there is sequential consistency. So in the rest of this lecture, I'm going to define a bit more precisely the different terms here, but this is just since you guys asked for an overview, then this is it. And then another thing is I've realized that I didn't quite understand initially the question about PN counters. So now I reread it in the chat. So it's kind of interesting. So the question was, if you have essentially you're doing garbage collection by reference counting, and you're using a counter implemented as a CRDT with additions and subtractions. So can you garbage collect an object if this counter goes to 0? And the answer is no, because if you read the state of an object, it gives you your local view based on whatever updates you received. There may be some updates at other replicas that you're not aware of. So if your counter now is 0, so that means that the number of increments is equal to the number of decrements out of what you see. It doesn't mean that there is no increment somewhere else that you're not aware of. So maybe someone is still using this resource and you just don't know about it. Eventually you'll find out, but later. Okay, so you kind of have to be, kind of illustrates that you need to be careful when using CRDTs. Okay, so let me continue. I'm going to be talking about axiomatic specifications of these kinds of models. So let me recap. This is the stuff I introduced a bit earlier using an example of our sequential consistency. So to specify a consistency model axiomatically, I need to choose a set of binary relations over events, so R1 to Rn, that declaratively specify how the database processes operations. Then we have a notion of an abstract execution, which is a tuple of a history and a bunch of relations like this. And then we choose a set of axioms over abstract executions, and the consistency model is defined as the set of histories such that I can pick some witnesses for these relations, R1 to Rn, and the resulting abstract execution of the history with these relations is going to satisfy my axioms. So in the sequential consistency case, there was just one relation, TO, which was the total order on all operations in which the server processes them. And there were two axioms. One was that the session order is included into the total order. So the order in which the server processes requests is consistent with the order in which clients submit them. And the second axiom defined how the return values are computed in terms of this order. And so now to do the same for weaker models, I'm just going to pick different relations and different axioms, in particular because we don't have strong consistency anymore. Instead of a total order, I'm going to have some partial orders. And then the axioms are going to be of the same two kinds. So there's going to be some inclusion axioms that say that one relation is included into the other, and they're going to be used to disallow anomalies of the kinds I showed to you before. And then there's going to be one axiom that specifies how the return values of operations are computed, and that's going to depend on the semantics of replicated data types. So I'll have to define that as well. Okay, so that's the overview of what's coming. Okay, so here is how an abstract execution is going to look like for these weaker models. In this case, I'm going to have a history, which is a set of events. So as before, these are events consisting of an object, the operation that I'm doing, and the return value that I get. The session order, which is the order in which clients submit the requests. And so I'm visualizing here everything in the same way as I did before by this graph with a bunch of relations. And then the interesting part is that there are these two new relations, vis and AR, so that stands for visibility and arbitration, that are meant to declaratively specify how the database processes requests in a weaker model like eventual consistency. So let me explain what these relations are. So let's take the visibility first. So I'm going to explain it in terms of operational model just to give you an intuition, even though these are just some relations that are existentially quantified in the definition of consistency model. So the idea of visibility is the following one. So let's say I read access our object and I get all. So this is our old example of a bad social network with denying access to photos to your boss. Now, why am I reading all here? Well, it really depends on what kind of updates at other replicas I got to know about when I executed this read. So it depends on whether or not I'm going to read all, depends on whether this write of all has been delivered to this replica before this read was issued. And so this kind of a delivery guarantee is going to be abstractly represented by a visibility relation. So you have a visibility relation from this write to this read. So this visibility relation in implementation terms holds if the effector of this write has been delivered to the replica performing this read before the read was done. And so this is the visibility relation. So here I have a visibility from write of all to read of all. That's why I read all. And I have visibility of write of photo to the read from post, and that's why I read photo from this post relation. And this relation has to be irreflexive and acyclic to prevent kind of stupid types of graphs. And now there is another, and by the way, so the what is read depends on this, is going to depend on this visibility relation. So here, if I had a visibility relation from this write of no boss to this read of access, then my axioms are going to ensure that this read is actually going to return no boss, not all. Okay, and now there is this arbitration relation. So arbitration relation is about timestamps. Before I used timestamps to resolve conflicts, for example, in the case of a register. So there was this type of a picture where you did writes of 1 and 2. They got assigned some timestamps, T1 and T2. And depending on how these timestamps are ordered, you got conflict resolution one way or another. And so the arbitration relation in implementation terms is going to capture the ordering on the timestamps. So two operations are going to be related in the arbitration if the timestamps that the implementation assigns to them corresponds to this order. And so now here I have an arbitration relation from a right of all to right of no both, and intuitively that's meant to say that the right of no both should supersede the right of all. If I see both of them, I should read the no both and not all. And of course, I need some sanity checks on this relation. So this AR relation has to be total, so everything is related. It's a binary relation on the set of events, and also I want to ensure that visibility is included into arbitration. So if some update is visible to another one, like this right all is visible to no both, then no both is gonna get a bigger timestamp, higher timestamp than all. Now this is the notion of an abstract execution. Now I need to define a bunch of axioms constraining them. And the first axiom is determines how the return values are computed. So that of course depends on the data types that I use, or what kind of CRDTs I use in my system. And so there's going to be an axiom like this. Let's take this read of access that returns no both. So it sees these two rights, no both and all. So these are operations on the same object, and really these are the only operations that are important in determining the value of this read, because all the other operations, they're on on different objects, or they're invisible to this read. So what I can do is I can take this abstract execution and project it onto what we're going to call the context of this event E. So this is the projection of the execution onto all actions that are visible to this read, to this event E. And so this is our context. So let me erase the rest of the execution. And then the data type specification axiom is going to just say that the return value of an operation is computed based on the context of this event. Right, so the return value of E is computed based on the context of E using some magic function f, and the function f defines the data type specification. So it depends on the type of the object accessed by the event. So I can take the event, take the object that it accesses, and then take its type, which is the CRDT that I use. And for this type, I'll need to define this function f that, given a context of an event, returns the value of E. So in this example, given these two rights with these relations between them, what kind of value this read is going to return. So this definition is parametric in the data types I use, so I'm going to have to define a function f for each data type. So for last write to wins registers, it's very simple. What I need to do is to sort all actions in the context according to arbitration, and then return the last value written. So that's why here I'm reading no both. Here I'm reading no both and not all, because no both supersedes all. And what depends on what's taken into account when computing return values depends only on this. So what this axiom does is it takes the whole execution, and if you're interested in the return value of an event E, it projects the execution onto what's visible to this event and throws away anything else. So here, if I had an execution where this read, the only right that was visible to it was this initial right of all, then this axiom would say that you have to return all and not no both. Okay, so now let me go over a bunch of our specifications of data types. So these are going to be essentially slightly more declarative ways to say how these data types function than the implementations that I showed to you before. So here is one for counter. So that's very simple as well. What you do is you take the context that you have. So I'm doing a read. I take all the additions that this read sees, so these three additions, and then I return the sum of all these additions. So in this case, there are three additions, 1, 2, 3, so I return 6. It's very simple. In this case, if I have any kind of relationships between these additions in the context, say this addition is visible to this one, it's not actually used because it's a particularly trivial specification. But here is a case where it's going to be used. So I mentioned this multi-valued register before. So this is a register where if you have a conflict, then you return this expose this conflict to the user. So you don't just overwrite one right with another one. You tell the user, here is a set of rights that were done concurrently, please do something. So the type of a read here is that a read returns not a single value, but possibly a set. And so the semantics here is as follows. So let's say we have this example where there are three writes. I write 1, 2, and 3 to object X. And I also know that there is a visibility relation between the write of 2 and the write of 3. So that means when the user did the write of 3, he was actually aware of the write of 2. So when he did this write of 3, it was meant to really overwrite the write of 2. In contrast, write of 1, there is no visibility relationship between write of 1 and write of 3. So these two writes are concurrent. So when the user did the write of 3, he had no idea about write of 1. So this is really a conflict. And so the specification in this case is going to say that take all the writes that are visible to some other writes in the context and kick them out because they're really overwritten. The user is meant to overwrite them. So in this case, write of 2 gets kicked out. And then everything that's left, like for example, this pair, you return it. Right? And so in this case, it's going to be 1 and 3. So 2 kick out because it's superseded by 3. And 1 and 3, they're not superseded by anything, so you return the set of them. And so in this case, you tell the user, hey, there was a conflict, there were concurrent writes of 1 and 3, so do something about it. Okay, and now I can, right, and then for example, if I had a visibility edge from 1 to 3, so 3 actually was aware of 1, then I would just return only 3 because there is no conflict in this case. And now using the same trick, I can actually very easily define the semantics of an Edwin set. So let's remember our previous or artificial example where there were 2 editions of the book. And so these editions actually, there was no visibility edge between them, so they were unaware of each other. Let's say 2 people added the book at the same time. And then there is a removal of the book, and the removal sees this add. So the user who did this removal, he first read the contents of the set, so this addition, and then it was he meant to remove it using this removal. But on the other hand, this addition over here was done concurrently with removal. And so the semantics of an Edwin set says that the removal should have no effect over concurrent additions. And so in this case, to define this function f that determines the result of this read is going to be pretty similar to the multi-value register. You take all the additions that are superseded by a removal of the same element in visibility relation and kick them out of the context. So this addition is gone. And all the remaining additions that are not visibility related with any removal of the same element, you leave them and you return whatever is left. And so in this case, I will return the book. And if I had a visibility relation from this addition to this removal, then I would return an empty set because in that case, the removal is not concurrent with any of the 2 additions. So it's really meant to erase them. Okay, so that's the data type specification. And so again, this function f, the type of it is that it takes a context and returns a value of e. And notice that it was quite easy to specify, for example, an Edwin set in this way, whereas before I spent many slides describing to you this abstract implementation that uses identifiers under the hood and things like that. So this is one of the benefits of the axiomatic specification, that you can do it very concisely. And then all you have to determine return values is this axiom that says the return value of an event E is computed on the context of this event based on this function f that I've just defined. Okay, and now this is one axiom. There's going to be a couple more axioms to define eventual consistency that are sort of sanity checks, so they just disallow stupid things from happening. First of all, there is this axiom that kind of says no causality cycles. So I want to disallow cycles in the union of session order and visibility. And informally, that's true because both session order and visibility, they're consistent with the notion of real time. So if I happened after something in session order or in visibility, then I really happened after that event in real time. So it would be kind of strange if I tie the cycle. So in particular, I can't have this kind of cycle on the slide where I have a cycle like SO, then this, then SO, then this. So I'm going to now explain a bit what this example is about. So these kinds of examples, they could result from speculative execution. And weirdly, this is actually allowed in some shared memory models. So if you take some processors like ARM or languages like C++ and Java, then they don't allow exactly this example on the slide, but they allow some similar things, and that leads to many complications. Fortunately, we don't have to deal with it in distributed systems, so we're just going to have SO union this to be acyclic. Now, just to explain this example, the way this could happen if I had speculation is something like this. Here, the first process reads X, and let's say the read takes a long time to complete. So it says, well, let me guess, maybe it's 42. Let's see, what would happen if this were 42. Well, then the next statement says, write what you read into Y. Okay, so I write 42 into Y. Then this update gets sent to some other replica who reads Y and gets 42. Well, this replica says, okay, fine, so I'll execute the next statement. And the next statement says, well, write what you read into X. So you write 42 into X. This update gets delivered to the original replica, and the guy says, oh, I got 42, so my speculation was correct. So fine, everything is all right. So that's the kind of behavior that we don't want to do, because I could put here any value instead of 42, so people call this out of thin air values. And so that's the reason that I'm going to have this axiom. And now there is another axiom which sort of defines the word eventual in eventual consistency. So informally, it says that any update will eventually be propagated throughout the system. So what I don't want to happen is there is a user who does a write of 42 to X at one replica, and then there is a user who keeps reading X at another replica and never sees the update by the first user. So she keeps reading zeros here. So I don't want this to happen. And from the implementation perspective, that's because eventually this update of 42 will be propagated everywhere. So eventually all the partitions are going to heal. And that means that I should really see 42 at some point. To specify this, I'm going to have this axiom that says that for any event E, so in this case, write of 42, there may be only finitely many events F in the execution such that E is not visible to F. And so that means that I cannot, yes.
Yeah, just sorry for a quick question from the audience. So the visibility relations, could you maybe just recall where it comes from? So what identifies visibility? So
there are two answers. It's really it comes from nowhere. It's if like for a really formal answer, it's existentially quantified. So let me just this is the whole specification. So So if I want to define eventual consistency, then I'll take the set of all histories E and SO, such that there are some visibility and arbitration relations such that these axioms are satisfied. So this visibility, like on the formal level, when I define the specification axiomatically, is just existentially quantified. So to check if some outcome, some history is allowed, I need to figure out some visibility relation satisfying all the axioms. Okay. Now, intuitively, I kind of try to explain where it comes from in the implementation. So in the implementation, it would usually come from message deliveries. So the reason why some outcomes are going to be allowed on eventual consistency is because some messages are going to be delivered, and that will give you visibility relationship. So that's the slide that I showed before. So over here, this write is visible to this read because there was a delivery of this message to this replica before the read was issued. Now, this slide is pure intuition. This is an informal explanation. If you want to formalize this to state it a bit more precisely, then when you prove a soundness of the axiomatic specification, so you prove that any behavior allowed by the implementation is also allowed by the axiomatic specifications, you would need to construct visibility out of the operational execution of your implementation, and you would construct it in this way, as I showed on the slide. So Piotr, does this, do you think it clarifies
Well, I hope.
things?
Does the same go with the arbitration?
Yeah, it's the same thing. So arbitration, so again, the axiomatic specification is a very formal construct. You just say there are some extensively quantified relations. They satisfy these axioms. What they are, well, I don't know, like some relations. Like the intuition comes from these kinds of from this kind of reasoning about the implementation.
Okay. Well, let's move on.
Okay. Okay, and so there is this eventual visibility axiom that says that for any event E, such as this right for 42, there may be only finitely many events F that don't see this event. And so that means that I cannot have a history like what is shown on the slide. Eventually, I will have to have visibility edges from this right of 42 to the reads in this session, and then they will have to return 42 because the return values are computed based on visibility. Okay, and so this is the summary of eventual consistency. So it's the set of defined axiomatically. So it's the set of all histories ESO such that I can pick some visibility and arbitration relations that satisfy these three axioms. The return values are consistent with the data type specifications according to this capital function F. There are no causal cycles, so session order using visibility is acyclic, and there is this eventual visibility axiom saying that every update eventually is visible to all clients. And this is a bit of a more precise definition than quiescent consistency, but it implies it. So quiescent consistency, remember, said that if no new updates are made to the database, then replicas will eventually converge to the same state. So this is a bit doesn't quite fit in here because it's defined in terms of implementation concepts like deliveries and replicas, but I can rewrite it a bit more declaratively. So I can say that in an execution with just finitely many updates, all but finitely many operations on a given object will return values computed on the same context, which is all the writes in my execution. And so I think I'm going to leave as one of the exercises on the web page to actually prove that this definition of eventual consistency implies this definition of quiescent consistency. Okay, that's it with the axiomatic definition of eventual consistency. I know if there are more questions, then I can answer them. Otherwise, I will go on.
Yeah, maybe just a suggestion to go over the last slide over again, just to make sure we understand what your formalism actually is saying.
Okay, so. So it's actually these kind of definitions are kind of difficult to understand because of this existential quantification. So again, I need to define a consistency model. So I define a consistency. So consistency model is a set of histories, right? So the set of allowed executions, allowed behaviors exposed to the clients. In this case, a history is a set of events and the session order the order in which clients submit these operations. And now I need to determine is a given history eventually consistent or not. And this is done parametrically with a bunch of data type specifications that I have. So I have a database that has a bunch of CRDTs in it, and so I have these functions capital F that specify the semantics of the CRDTs. And so to determine if such a history is eventually consistent or not, I need to find witnesses for visibility and arbitration relations. So these are existentially quantified here for some. I can pick them in any way as long as they satisfy all these axioms and, of course, all the basic properties that I said before, like these are cyclic relations and stuff like this. And the axioms just say that for the first axiom says how the return values are computed, that the return value of each event E is computed on its context using the data type specification function F. And remember, the context is the projection of the execution onto everything that's visible to this event E. So I just take an event, take everything that's visible, feed it into this function F that tells me how I resolve conflicts and gives me the outcome. So it just says the outcomes in this history are consistent with the data type specifications. then this is just a basic sanity check that there are no strange cycles in this graph. And then the final axiom is just the meaning of the word eventual, that eventually every event E is going to be seen by all the events F. And then this quiescent consistency, the way I formulated it here, it's a bit of a mouthful, but okay, let me try to go over it again. So quiescent consistency is only about executions with finitely many updates. If you have infinitely many updates, then all bets are off. So you have to have a history where out of this E, there are only finitely many updates. The rest are read-only operations. Then I fix an object. And what quiescent consistency says is that there will be finitely many operations on this. There may be finitely many operations on this object that return strange values, but apart from that, those operations, the rest of the operations are all going to be computed. The results are all going to be computed based on the same context. So if I take all these operations E, look at their context. Intuitively, their context is going to be all the updates in the executions. Because there are finitely many updates. Eventually they're visible to everybody, and so eventually whatever event you run it's going to see the same context with the same set of updates. And that means if I execute the same operation, I'm going to get the same return value. Okay, so this is maybe an unzipped version of my explanation before.
Okay, well, just one more minor question. So when you talk about contexts, so here you assume that this function f, which operates on functions, on contexts, and which provides the state of the return value of an event. So it's basically this function only operates on the updates which are contained in the context.
I didn't require this, but any sensible function would only take into account updates.
Yeah, but when it comes to your exercise, where
the exercise will need to, so there is, I need to spell out the terms and conditions. Yeah, the exercise you'll need to assume that if you take a function, any function you consider, take a context, kick out all the read-only operations, the return value doesn't change.
Yeah, and the other thing is also, I guess you implicitly assume that arbitration is the total order.
Yeah, I just didn't spell it out, but this visibility and arbitration here, they're meant to satisfy all these conditions. Visibility is acyclic, arbitration is total, and also acyclic, so things like that.
And can you what is the relation here between your new definition, more technical definition of eventual consistency, and quiescent consistency? Quiescent consistency is like a special case of.
So this is stronger than quiescent consistency. So the exercise would be that you can actually prove that what's in the box implies quiescent consistency. It's a bit awkward to formulate quiescent consistency over this formalism, but it can be done.
Okay, but not vice versa.
Not vice versa.
Okay, just 1 second. There was one more question. Where does the requirement of not having causal cycles come from? Okay, again, can you maybe elaborate a little bit on the requirement of not having cycles in the union of session order and visibility? So why is it important, and what exactly it means? What it means in practice?
So in practice, this means that you cannot get, so it's like a basic. So where it comes from? Well, any sensible system that is implemented nowadays would not give you these kinds of cycles. Okay, and if you allowed them, then you would get into these kind of strange situations where you have this execution, and it would be valid no matter which value I stick in here. So it doesn't have to be 42, it can be anything, right? So people say out of thin air values. And there are difficult questions related to this in shared memory models, like what multiprocessors provide. But in distributed systems, they don't do these kinds of things. So I'm not aware of any database that would produce this kind of an execution.
And your example for the shared memory model, assumes that you have potentially you can have multiple writes of the identical values. So written values are not uniquely identified. So do you think it's an important property and requirement that if you say, for example, that all written values are identified uniquely, so some anomalies would go away automatically?
This is not really about uniquely. I'm not sure I understand your question. This is not about unique unique rights. This is just, yeah. So the problem is that I can stick. No, the problem is it's not the fact. Like the problem is I can this execution is gonna be like if I allow these cycles, this execution would be valid no matter which value I stick in here. So the reason why it's problematic and share. So okay. So I kind of don't want to get into too much into this, but so shared memory multiprocessors, what they would do is if there is if this write of y is to 42 to y is unconditional, so you write 42 no matter what you read here, they would actually do it speculatively before you finish this read. So in this case, it's sort of okay because so it's a cycle in SO union this, but it's sort of okay because our 42 was actually in the program, so at least it's not an arbitrary value. But it's currently an open problem to define these okay causal cycles are so in the C++, at least on the programming language level. So in the C++ memory model is still an open problem. But in the distributed systems, at least the modern ones, usually you don't do these speculations. So you can just this axiom was just going to be true.
Okay, and so one maybe last question again on your definition of eventual consistency. So your the only information which comes from what really happened is the session order, or the set of events and the session order. So some more advanced criteria such as linearizability, they also sort of borrow from the actual execution, the real time, the real time relation between operations. So do you think it's a variant of eventual consistency with which also takes into account the real time order?
Yeah, there is a I kick things out to make the course manageable. Like there is a co-author of mine, Sebastian Burkhardt. He wrote a whole book, so you can find it on the reference page, and there he actually has histories with real-time order, precisely because he wanted to define linearizability as one of the models. So, and you can also have weak variants of weaker models that respect real-time order. So I didn't do it just because I didn't want to complicate things, but you can do it. So the intention of a history is that it exposes everything that's visible to the users. So in this case, it's you assume that it's events and session order, and the users cannot track the real-time order, meaning they cannot communicate out of band except for through the database. But you can extend this if you want to.
Mm-hmm. Okay, and also you may incorporate some notion of causality between events.
Well, that's kind of incorporated via visibility, via this existential quantification. But you could. I think real-time order is like a very coarse approximation of external causality. That if A happens before B, then that means that there was an opportunity for A and B to communicate, and so B has to be aware of A.
Yeah.
Okay.
Okay, well, thanks.
Okay, so then I'll go on. Okay, so now let me come back to the zoo a bit. So what I've defined is just an eventual consistency. So it says it's stronger than quiescent consistency, but it's still pretty weak because visibility and arbitration, apart from satisfying some basic sanity checks that no causal cycles or they're not acyclic or total orders, there are no other constraints on them. So in particular, all kinds of anomalies may be allowed. And so what's nice about these axiomatic models is that now I can very easily strengthen this kind of a model by just adding additional axioms constraining visibility and arbitration. So here's my consistency zoo. So it's very small. Actually, there are many more species, but again, I want to keep the course manageable, so I'll stick to these. So let me just define a bunch of these things. So first, there was this read your rights guarantee that I told you about before. So the problem here was that the same client does an addition of 100 to a counter, then reads the counter later in the session order and sees 0. And I said this could happen in some implementations if these two operations went to different replicas. And so you can easily specify a read your rights guarantee that disallows these kinds of anomalies by just requiring that session order be included into visibility. So that if a client did one operation and then later did another operation in the same session, then the second operation sees the first one. So everything the client has done so far in the session. And so there are many more guarantees like this, or the class of them is called session guarantees. Essentially, they guarantee to you that clients only accumulate information as they go through the session. They never lose it. So here is, and it can be implemented if the client just sticks to the same replica. And here's another one of guarantees for this kind. So it's called monotonic reads. So it's the same thing, but instead of taking into account updates that I do in the same session, I take into account the updates that I saw in this session. So for example, let's say somebody did an addition of 100 to a counter, then this got propagated to the replica where I am, and I did another 100, and then later I'm reading the contents of this counter. And in this execution, I see 100 and not 200 because my addition is visible to me, so read your rights is satisfied, but this addition is invisible, even though my addition was already saw it. And so this can be disallowed if I only ensure the visibility edge from this addition, the first one, to this read. So in this case, I would read 200 according to my specification. And so this can be specified by just ensuring that the sequential composition of visibility and session order is included into a visibility. So if I have a visibility edge into some event in my session, so this event sees something, that anything following this event will also see it. Right? And so in this case, it's vis and SO, and then I end up with this vis edge. And in the implementation, again, it can be ensured if the client just sticks to the same replica, because the first addition that it does already sees the previous addition. So if it sticks to the same replica, all the next operations are also going to be aware of it. Okay, and now there is causal consistency, which disallows this strange anomaly with poor employee who are messed up access permissions. So this is our previous execution. There was the right of all to access, which is the default value. There is a right of no boss that supersedes it, so denies permissions. Then there is a right of photo to post. And then there is a read of post that gets the photo, and read of access that gets all, and that's because there is only a visibility edge like this one to all, but there is no visibility edge from the no boss to this read. And so the unintuitive thing here is that there is a chain of session order and visibility edges. So this, and this, what's highlighted in red, from the right to no boss to the read of access. And so in this case, people say that the right of no boss happened before the read. And what we need to do to disallow this anomaly is to mandate that all actions that happened before some action be visible to it. And so this can be done by just requiring that the union of SO with this and their transitive closure is included into this. So this union, the transitive closure of session order and visibility is called the happens before relation. So intuitively, it represents causality relationships in your system. And then here, if I require this axiom, this chain of red edges will mandate to me this visibility edge from no boss to the read from access. And that means that I can't read all here. I need to read no boss. And this definition, of course, implies session guarantees because, in particular, it implies that SO is a subset of Viz, and the sequential composition of Viz and SO is also a subset of Viz. So causal consistency is kind of quite a nice model. Now, unfortunately, the implementations are, at least if you want to implement it efficiently, they're quite complex. It's been an active research area in the last few years, so I don't have time to talk about them. So these informally speaking, these implementations have to track happens before predecessors of each update to ensure that you don't have such anomalies. But again, the nice thing about our axiomatic specifications is that to explain what causal consistency is to you, I don't need to explain to you all kinds of difficult implementations. I can just write down this one axiom that says it all. Okay, so let me just illustrate what is allowed and not allowed, for example, by causal consistency. This is our previous Decker example. So there is there are two processes axing objects x and y, and here the first process writes 1 to x, then reads 0 from y, and here you write 1 to y and read 0 from x. So in this case, both processes win. So on sequential consistency, I showed that this is impossible. On causal consistencies, this is actually possible because I can draw the visibility edges consistent with the session order, so this one, and that's it. So that's all the visibility edges that I'm gonna add to this execution, and this actually satisfies all the causal consistency axioms. The causal consistency doesn't buy you anything in this case because there is no transitive closure of SO and Viz will not produce any more edges, and the return values are okay because here I read 0 because I can't see this right to y, and I read 0 from x because I can't see this right to x. And so this is actually a valid causally consistent execution. And in an implementation, this could happen if the deliveries of these writes are just delayed. So these two clients, they work at different replicas, they do the writes, then the writes take a while to get delivered to the other replica, and before that the processes do the reads that don't see their counterparts right. So you gotta be a bit careful when you program on these models. Okay, and also just to complete the zoo, I can also specify sequential consistency in the same framework. Also, before I did a special definition with some total order TO on actions. Actually, here I can specify the same by just requiring that visibility is total. So kind of cook up a total order out of visibility, and also that, of course, session order is a subset of visibility. And alternatively, since I required before that visibility is a subset of arbitration, then I can equivalently require just that the visibility is equal to arbitration and the session order is a subset of visibility. So in this case, the structure of abstract execution kind of degenerates into just one total order, which is what we saw before with sequential consistency. And then the data type correctness axiom just says that every operation sees the effects of all operations preceding it in visibility. So really, in this case, visibility, arbitration, and this total order that I introduced before for sequential consistency, they collapse into the same thing. Okay, and then with the Decker example, before I showed that it's impossible on sequential consistency, so here I can do the same thing using this axiomatic execution. So again, I can draw a history like this, right, with the writes and the reads and the session order edges, and then the session order has to be included into visibility, so I have to draw visibility edges as well, and then visibility has to be total, the way I've just defined sequential consistency. That means that for any pair of a write and a read, I have to draw the visibility edge one way or another. So this read returns 0. That means it cannot see this write, because then have to return 1, and so I must have a visibility and also arbitration edge this way, and similarly I also have to have a visibility edge this way, and now I get the cycle in visibility, which is impossible because I required visibility to be acyclic, and so in this case I say that, okay, there is no abstract execution with such a history, so on sequential consistency this example is actually not allowed. Okay, and so now our consistency zoo is specified using these kinds of axioms. So eventual consistency is the definition I showed to you before, which is the baseline. So it's included, all the axioms there are included into all other definitions. And then I get stronger consistency models by just including more axioms. So for session guarantees, I have some inclusions that say that SO is included in this or stuff like this. For causal consistency, I have something stronger, that the transitive closure of the union of SO and visibility is included into visibility. And for sequential consistency, I just require that visibility arbitration are the same and there are total orders. And as I go stronger, then I disallow more and more anomalies. So for example, session guarantees, they allow both the Decker example and the causality violation. Then when I go to causal consistency, causality violation is disallowed by Decker stays, and in sequential consistency, both of these anomalies are disallowed. So these are the definitions. Now, one nice thing is that because these definitions are they are independent of the implementations, I can actually get some interesting theoretical results that are just about consistency models and apply really to all possible implementations. So in particular, okay, I'll come back to this later. So in particular, one question is, I proved this CAP theorem that says that sequential consistency, you can't implement it if you require immediate availability and partition tolerance. But then there are all these other models, right? So which ones of them are implementable while with immediate availability and partition tolerance, and what is the best one you can do? For example, like I can show that all of them are actually implementable because they all don't do any synchronization. But for example, is causal consistency the strongest one, or can I go even stronger? So I didn't show you the whole zoo, but here there are some intermediate models. And actually there is a recent paper that shows that causal consistency is actually a strongest such model. So this is a model that cannot be strengthened if you want to satisfy high availability and partition tolerance. Now there are some terms and conditions as usual with these results. So it applies to a certain version of causal consistency and certain class of implementations. And also when I wrote a strongest such model, that's not a mistake in English, because it means that this model cannot be strengthened, but there may be other incomparable models that are also implementable with high availability and partition tolerance. But at least this gives some justification that causal consistency is a nice model. And then there is another result, which is kind of curious. I mentioned many times this example of collaborative editing, so things like Google Docs or Office online. And at the core, these are really implement a list data, replicated list data type. And so what you can prove if you specify list data type in this framework is that this data type, its implementation actually has a very high metadata overhead. So if you want to implement it in a reasonable way, you actually can't ever discard a character when deleting it from a Google Docs document. So I kind of won't have time to explain why, but it's a surprising result. And that means that, of course, you can't afford to keep these characters forever. So that means that at some point, if you start discarding them, it may be possible that if some users reconnect with really stale sessions, they will see previously deleted elements. So these are the kinds of trade-offs that you have to make in these systems. And finally, I mentioned several times also shared memory models. So all these consistency issues also happen there. In fact, sequential consistency was first proposed in the context of shared memory by Lampard back in '79. And nowadays, both multiprocessors and programming languages, for them, they actually don't provide sequential consistency. They provide weak memory models because of both processor and compilers optimization conversations. And the style of axiomatic definitions that I showed you is actually one of the de facto standards for defining these kinds of models. And in particular, if I specialize my specifications to last write to wins registers, which is the closest we get to a shared memory, then I get something very similar to existing shared memory models. In particular, our causal consistency corresponds to something that C++ calls release acquire, which is one of the types of consistency that it provides. Okay, and so that's it with this fragment. Any questions, or shall I continue?
I haven't seen it.
Okay.
No, I think it's okay. Yeah, maybe if you can just come back quickly again. So you have this in the definition of eventual consistency. You use two partial orders on events. Yeah, well, one partial, one total. Yeah, you use partial visibility relation and you total arbitration. Just again. So you're in case you want to look for strong consistency, which you call sequential consistency. These two are the same. Essentially, you're looking for a total order.
Yes.
In the case of eventual consistency, it's important to have this partial visibility relation to exist. And could you maybe just, again, in this particular context, say where exactly you use the arbitration order?
The arbitration is used just if you use some conflict resolution mechanisms based on timestamps. Then arbitration declaratively specifies what they do. So it's just that, but the thing is that visibility and timestamps are different things. So visibility is which messages got delivered. Timestamp is what kind of timestamps you slapped on them. But you could have slapped wall clock time, or maybe it's Lampard clock. But if something gets a higher timestamp, it doesn't mean that you will necessarily see it and stuff like this.
So would it be correct to say that this arbitration relation is hidden in this function f, which you use for computing the return values?
It's used there, right? So if I specify the read-write register, then so it's the only place where it's used. I could define some. So in this causal consistency, I could define that AR is consistent with causality as well, like if I want to. But really, in the basic definition, the only place it's used is this function f. When I define it, for example, for read-write register, I will look at the context and take the last event in arbitration.
Okay. No, thanks. There is one more question. Could you repeat the implications for Google Docs again? What do you mean by deleting characters?
You delete characters in Google Docs, right? You press backspace and the character is gone. Now the problem is that I'm not going to be able to get into the details, but you can read this paper if you're interested. So the problem is that these deletions and additions, they're processed synchronously. So in particular, essentially, okay, so let me explain it like this. So you press backspace and you delete a character. Let's say you're synchronizing, right? So if you really completely discard this character, right, then what can happen is, if you get another copy of a document that somebody is sending you, that still has this character that you deleted. You need to remember that you deleted it so that this is not a new insertion. This is the one you deleted. So really, you should let that guy know that the character was deleted. So really, in the implementation, you need to maintain what's called a tombstone. So you kind of maintain that I had this character over here. Maybe you don't need to know what character it is exactly, but you need to maintain some kind of an ID or metadata. There was this addition with this identifier at some point. And now if I get a document that has that character, I should just delete it and not interpret it as a new addition. And the problem is that if you can always have a user with a really stale copy that has that character still present, then you can never be sure when you can discard this tombstone. So I did my best to explain.
Yeah. Okay, thanks.
Okay, so I'll have to skip one segment. So I just want to say I'm just going to say a few words and then jump to something else. So I presented to you these two types of specification, axiomatic and operational. Really, you need to prove that they say the same thing, so that this axiomatic specification is sound, so it captures all the behaviors allowed by the operational implementations. Which are close to implementation, so operational specifications which are close to implementations, and so there are actually techniques for doing these proofs. And unfortunately, I'm not going to have time to cover them, but I can also leave these slides, and then you can, if you're interested, you can have a look at them offline. And so I'm going to switch to something else, which is the last part of this course. Okay, which has to do with determining the right level of consistency. So there is this zoo of consistency criteria, and so the question is, well, which one should I choose for my application to be correct? And whichever criteria you choose, if it's not with strong consistency, you'll expose some anomalies to the users. In some cases, anomalies are fine, but what you really don't want to screw up is some basic properties about the integrity of your data. For example, that account balance is non-negative if it's a bank account or all registered students are enrolled into a course. So these kind of properties are called integrity invariants in databases. So this is something pretty important. And the challenge here is that the vanilla weak consistency, so if I take any of these consistency conditions that allow partition tolerance and high availability, they're going to be often too weak to preserve correctness. And to really keep correctness, you need to strengthen consistency in parts of the application. And the keyword here is parts, because, okay, you could run the whole application on sequential consistency, but that's expensive. So ideally, you want to pay additional cost only when necessary. So let me explain to you what's going on here by example. So let's take this bank account example. So the integrity invariant says that the balance is non-negative. So I can implement deposits using this addition operation on counters. So just to recap, this picture is our previous semantics of replicated data types. So if I add 100 to my bank account, then I initially do it at one replica, say this one. So I perform this operation of addition here. And then later I propagate the effector of this operation to other replicas. So the effector in this case is a function that adds 100 to the balance, sigma prime, of the account at the destination replica. And then this effector, when it's applied to the state sigma prime at this replica, is what's going to determine the account balance there after it receives the deposit. So the deposits are quite simple. They just add 100 to wherever they get to. Now, with the withdrawals are trickier. So let's see how we could implement withdrawals. Let's say I want to withdraw 100 euros from my bank account. Now, originally, I do this at some replica that has a state sigma. And then how can I define the effector? Well, so look at the state sigma. First of all, I need to do a check. Is there enough money in the account, at least at the source replica? So I have to check if sigma is greater than or equal than 100. If it is, then I'm going to create an effector that's going to subtract 100 to wherever it gets to, right? So if a replica receives it and it's in some state sigma prime, then this effector was going to say, okay, subtract 100. And if there is not enough money left in the account at the source replica where I originally tried to do withdrawal, then the effector is going to be the identity function because there is nothing to change. And so now with this kind of definition, which is, I guess, the most sensible thing you could come up with, you actually get into trouble because, so let's say you have your bank account replicated in two places, at two replicas, and initially you have 100 euros in the account, and so both replicas say, okay, the balance is 100. Then what the two users can do is they can come to these different replicas and try to withdraw 100 euros. So this is a highly available system, so you have to respond immediately without communication. So the withdrawals are going to succeed because there is enough money in both replicas say there is enough money in the account. And then the effectors they're going to generate is the same function that says, okay, subtract 100 from the balance. So initially, they're going to be applied at the source replicas where they're executed. So the balance there is going to get to 0. And then the effector of one of them is going to get propagated to the other replica, and there the balance will be minus 100. So in this case, I've overspent money. And here there is really nothing you can do unless you're willing to synchronize. So I could, of course, run this whole system on strong consistency, but then deposits would also have to synchronize, and deposits really don't have to preserve this invariant that the account balance is non-negative. I can do them like at my replica and propagate their effects later. That's kind of how bank accounts operate in reality. And so the solution here is to tune consistency to make withdrawals strongly consistent and deposits eventually consistent. And in this case, I'm gonna optimize my performance so that I only pay for consistency where necessary. Okay, so I can actually specify this kind of a hybrid model very easily in the axiomatic framework. So I'm going to assume in the rest of the talk that the baseline model is causal consistency. So just to keep things simple, so it's a nice model, as I said before. And then what I have are this example I showed to you before. In terms of abstract executions, it's represented like this, where I have this graph with one addition of 100 euros, two withdrawals. These withdrawals see the addition, but they don't see each other. So these two withdrawals are concurrent. So the problem is that they're causally independent. And now if I want to make sure that they synchronize, then I can do it as follows. So I'm going to say that, so let's say we have a symmetric conflict relation on operations. So for example, two withdrawals are in conflict. So this is something that the programmer specifies. So it has a set of operations that says these pairs of operations have to conflict. And the axiom that I'm going to require is that conflicting operations, they cannot be causally independent. So if I have two events, E and F, and the operations performed by these events conflict according to this relation, then either E has to be visible to F or F has to be visible to E. There has to be a visibility relation one way or another. And so then this execution on the side becomes invalid because withdrawals they're not related by visibility one way or another. And so they have to be related at least one way. So for example, like this. But then if I relate them like this and look at the specification of how withdrawals are computed, then this withdrawal sees the deposit of 100, withdrawal of 100. So the account balance here is 0. And that means the withdrawal has to fail. The effector has to be an identity function. And so in this way, I can define my consistency model. And now the good news is that additions, so these deposits, I can have as many as I want. They don't conflict with any operations, either between themselves or with withdrawals. And that means I don't have to have visibility edges between them. And so I don't have to pay for the synchronization that these visibility edges imply. Okay, now this is a specification. I don't have time to talk about the implementation. It really requires fancy things like consensus and taxes. Again, the good news is just that you don't pay for it for additions. Let me just describe very briefly and intuitively how in principle it would operate. So essentially the way you can understand the implementation of this model is as if a withdrawal grabs an exclusive lock on the account. So if I'm sitting at a replica and the balance there is 100 and I want to do a withdrawal, then I grab a lock. So maybe my withdrawal is successful, but now if somebody else wants to do a withdrawal, they will have to grab that lock from me. And when they do this, I will tell them about all the operations that I did. And so in this case, the balance at the second replica is going to go down to 0 because it's aware of the withdrawal. And then the second withdrawal will just fail. So that's the intuition, and then the additions, they don't acquire any locks, so there's no synchronization there. Okay, so in fact, there are quite a few databases nowadays that give you these types of consistency choices, including the databases from major vendors. Of course, it's not free, so the stronger operations will require synchronization, and you will pay for them. with latency because they're slower, possible unavailability because you have to synchronize, you're not tolerant to network partitioning anymore for these types of operations, and even money. So in fact, Amazon Web Services would actually charge you more for a strongly consistent access than for a weakly consistent one. But if you choose them judiciously, so choose strong consistency only where necessary, you can actually minimize your costs. And so now the problem is that it's kind of non-trivial to reason about this, so it's hard to figure out the minimum consistency level that's necessary to maintain correctness. So on one hand, we have this abstract execution formalism that abstracts from many details of the implementations, but even so, the number of possible abstract executions of your program would be exponential in the number of events, because you can choose visibility edges in whatever way you like, subject to axioms. And so really, ideally, you would need a verification technique that would limit this exponential blob. And so since I have a verification background, in the remaining 20 minutes, I'll tell you a bit about a tool that we developed that does these kinds of checks. Okay, so the verification problem here is like this. We're given a set of operations. So somebody has his mic unmuted, just as a... okay, thanks. So we have a set of operations like withdraw, deposit, and all that, and the conflict relation on them. So, for example, two withdrawals have to conflict, and deposits don't have to conflict. And the question we're asking is, do these operations always preserve a given integrity invariant, like that the balance is non-negative, if you run them on this consistency model that I showed to you before, where conflicting operations have to synchronize. Okay, so let's think about how we would go about checking this. And the easiest thing to start with is just the sequential execution. So let's say we had a strongly consistent system, so it's as if you have one copy of your data. How would you check that the invariant like this is preserved? Well, you would do this inductively. You would assume that invariant holds at some point at this single replica. And then if you do an operation, you would have to check that this operation preserves this invariant. So that's it. And in this case, it's very simple because it's a single check. There is no state space explosion from concurrency. You just need to do one check per operation. So let's see what happens in the replicated case. So here the problem is that effect of an operation is applied in a state that's different from the one it was generated in, right? So if I do this operation op, I'm going to generate an effector for it, which is the function describing the update, send this effector to another replica, and then there would be another state sigma prime. And now I need to check that the invariant is preserved if I apply this effector in this other state, sigma prime, not the one in the sigma I was originally generating this operation from. So in the rest of the presentation, to just simplify things, I'm going to assume that these effectors are written in a particular form, which is actually how I've been writing them all along. So I'm going to assume that they're like done using these if-then-else constructions. So there is always a sequence of preconditions on the state of the origin replica, sigma, and then depending on the precondition, I generate different effectors. And so, for example, my withdrawal was like this. So I had a precondition saying, is there enough money left in the account? And then I had an effector that either subtracted 100 or gave an identity function. Okay, so now let's see how I can check that everything is going to be all right in this more complex case, given effectors of this form. So there are going to be two conditions. The first one is actually quite simple. It just says that the effector preserves the invariant given its precondition. So I have an effector f of sigma, which is one of these effectors generated in this if-then-else construction. It is generated under some precondition on the state of the origin replica p of sigma. So now I need to prove that if I execute this effector f of sigma in a state that satisfies the invariant and the precondition, then I'm going to preserve the invariant. So the state of the replica is still going to satisfy the invariant after the effector is executed. So this notation with curly brackets is something that verification people use. It just says that the curly brackets before a procedure are the precondition, what has to be true before, and the curly brackets after is the postcondition, what has to be true after. And so to look at an example, let's say we have our effector with withdrawal, so it subtracts 100 from the balance. Then there is a precondition saying there is 100 in the account at least, and there is the invariant saying that the balance is non-negative. Okay, so in this case, it's actually weaker than the precondition, so it doesn't bring anything new. And now what we need to prove is that if we execute this effector in the state satisfying the precondition, then the balance is still going to be greater or equal to 0 in the end. And that's of course true because we start with enough money in the account. And so this says that the invariant is going to be preserved at the target replica if only by the time I apply the effector, the precondition is true. In the precondition, we know that it was true here at the origin replica where I generated the effector. So the question is it going to be true over here when I have possibly different state sigma prime? And so there's going to be another, yes?
And just a quick question again from the audience about the effectors which do not change. About effectors which do not change the state of the replica. What is the point of introducing it into the formalism? Because from the implementation perspective, if it doesn't take effect, you can just drop it out. You don't.
It's just to simplify, purely to simplify presentation, because it allows me to say that any function, any operation has an effector. Otherwise, I would have to do case splits. Is this a read-only operation? Is it an update operation? But of course, in the implementation, you wouldn't send a message.
Okay. Thanks.
Okay, fine. And so now there is a second condition that's called precondition stability. So I'm going to explain what it is technically shortly, but informally, it ensures that the precondition P will hold at the time when the effector f of sigma is applied at any replica it gets to. So for example, here. Okay, so let's see how we can go about formulating this condition. So we know that the precondition was fine here at the source replica when the operation was issued. So the state sigma that I had here is the result of executing whatever this replica knew at the moment. The effectors all these operations that I denote by these blue circles, and these are all the causal dependencies of this operation op. Now, remember, I'm running on causal consistency, and there is a reason why I assume that, because that means that by the time this operation op gets to this replica also has to be aware of all the causal dependencies of this operation. So all these blue blue circles, they will also be here. They will be factored into the state sigma prime. The problem is that there may be some other effectors that this replica knows about and the original one didn't know about, and that's why the state sigma prime may be different. So these are the red circles. So now all the effectors commute, and that's what I assume. So that means that I can rewrite this as follows. I can say that the state sigma prime can be obtained from the state sigma by applying all these red effectors, f, g, etc. Right, and that's because sigma prime is obtained by applying all the effectors of all the circles over here. So I can apply the blue ones first. That's going to give me sigma, and then the red one second. That's gonna give me sigma prime. And now I know that the precondition was true of sigma. So if I'm midway through computing sigma prime, I just get to applying the blue circles, then the precondition still holds. Now the question is it going to hold if I additionally apply the red effectors? And so this gives an idea for how you could go about checking precondition stability. You could check that the precondition is preserved by the effector of any operation, because that means that no matter which red effector here I pick, the blue effectors, they satisfy the precondition. Then I go through the red ones one by one. If each one of them preserves the precondition, then I'm good. So let's see how it works in an example. Let's say the operation I'm dealing with is a deposit. So the effector is add 100 to the balance. And then the precondition is that there is enough money left in the account. So balance is greater than 100. And then I have to prove that the precondition is still true at the end. And it's going to be, of course. Now, the problem is that for withdrawals, it doesn't quite work. So if one of these red effectors is a withdrawal, and the operation op is also a withdrawal, then I need to prove that that the withdrawal preserves this precondition that says there is enough money left in the account, so greater or equal to 100, and that's not going to be the case, because I'm going to go down to 0. So now what's going on here is this condition is a bit too weak, and I need to strengthen it. And the way I'm going to strengthen it is I haven't yet used the fact that anything about conflicts. So I assume that two withdrawals have to synchronize. And so in fact, what I can show is that none of these red effectors can be conflicting with the operation op. And the condition I can formulate is as follows, that I need to check that the precondition P of an operation op is preserved by any effector of any non-conflicting operation. So if my operation op is a withdrawal, that means I don't have to check for stability against withdrawals. So I don't need to check precondition against withdrawals, but I have to check this precondition against additions. But for additions, it works, as I showed to you before, and my check will go through. So now let me explain why this is a sound condition to do. So I'm using the fact that withdrawals have to synchronize. So let's say this operation op is one withdrawal, and this red circle over here is another withdrawal. And so you have two conflicting operations. Now these operations have to synchronize. That means one of them has to be a causal dependency of the other. So let's say which way, let's just make a case split which way it goes. The first case is when the red withdrawal is a causal dependency of the operation op. But then in this case, the red withdrawal should really be blue because it's part of these causal dependencies that led to the state sigma. So this can't be the case. And then the reverse case is that our op is a causal dependency of this withdrawal. But then this violates causality because that means that the withdrawal, this red withdrawal, was delivered to the second replica before a causal dependency was delivered. So this operation op. So this can't be. Causal consistency doesn't allow that. And so that means that none of these red operations over here can be conflicting with the operation op. And so in particular, in our example, can be a withdrawal. And so I'm good. Okay, now the good news here is that checking this condition requires checking just each pair of operations. So you have a quadratic number of checks and you don't have any kind of an exponential state space explosion. So it's a bit worse than in the sequential case where there was a linear number of checks, just one check per operation. But it still are way better than an exponent. And so, in fact, you can automate these kind of checks using modern verification technology. So let me skip this. So in fact, we developed a prototype tool. It's developed by Srija Nair, who is a student in Paris, where you model applications of the domain-specific language, including replicated data type libraries, and then you discharge the conditions for this proof rule using solvers for satisfiability modular theories. So these are modern solvers that can automatically determine if a formula is true or not. And it also can automatically infer conflict relation, which is something I'm not going to have time to talk about. So let me just briefly show you in the rest of the talk how this works. So here I have a specification of a bank account in this prototype language. So here there are actually many bank accounts. So the state of the objects at the replicas is an array from clients to integers representing balances. So this is this square brackets is just a strange syntax for denoting arrays indexed by clients. Then the next line is some boring axiom that you need to give to the solver, so it's not interesting. And then here is our invariant. So that says that for each client, the balance of the client has to be always non-negative. And then there are two operations, deposits and withdrawals. So here you have a deposit where you're depositing an amount A1 into the account of a client C1. So the next line just says that it's going to modify the array of balances, and it has a precondition saying that, well, the amount you're depositing has to be non-negative. That's kind of this. And then this is a way to write an effector. So here it's written in a relational way. So you say that for each client, here is how we're going to modify the balances. If the client is not the one that we're depositing to, then nothing changes. So the balances of this client are going to be the same as their old value. And then if this is the client that we're dealing with, then its balance at the end, so that's balances of C1, is going to be equal to its old balance plus the amount you are depositing. So deposits are kind of easy, and then here is the withdrawal. So again, it says it's a procedure that withdraws are A1 from the account of client C1. Again, it modifies this array of balances, and it requires this precondition that I've been talking about, that there is enough money in the account. So balances of the client C1 minus A1, so the amount of withdrawing is still non-negative. And then this is again a relational specification of the effector that says that for each client, this is how we're going to change balances. If this is not our client, then the balances stay the same, so their value is the same one as the old value. And if the balances are, if this is the client we're dealing with, then the new balance of this client is going to be the old balance minus A1. And so this is the specification of the application, and now you can specify the conflict relation. So this is specified in this weird way because it's a prototype tool. So it just says that if there are two withdrawals, they're gonna be conflicting if they're on the same client. So here 1 and 2 are the numbers of parameters. So this is 1 is the first parameter of the first withdrawal, so the first client that you are dealing with, and 3 is the first parameter of the second withdrawal, so the overall parameter number 3, which is again the client ID. And so now what we can do is to run the tool. It actually takes a while because it does all kinds of other checks. So in particular, it checks that these effectors are actually commutative. And then after a while, it will it's going to do a bunch of checks. And then after a while, it's going to actually say that, yeah, everything goes through and this application actually satisfies the invariant. Okay, and so this says nothing, meaning everything has passed. And now I didn't have time to talk about this in detail, but just to demonstrate the power of this tool, what I can do is I can just erase the conflict relation the file with conflict relations that I gave to it. And so in this case, it's going to check the application without the conflict relation. It's going to find that the application is broken, and then it's going to find a sound way of repairing it by essentially generating this conflict relation that I showed to you at the beginning. So here it says that this precondition the important precondition failed, that there is enough money left in the account. And then it looks at this counterexample and generates this suggestion. So over here, that says that so essentially in the weird syntax, it says that two withdrawals have to conflict if they're on the same client C1. And then there are more examples that I could show you. I won't have time, but I'll probably leave some exercises for you to try applying this proof rule. Okay, and so that's pretty much it. So that's the end. So hopefully I've showed you that there is a lot of zoo and fauna in the data consistency, but using nice specifications, you can actually specify them relatively simply. And the weak consistency, of course, comes with downsides, a bit harder to program over, but this can be mitigated using verification techniques. And so if you have questions, then I'll be around for the discussion session, and also feel free to email me or look at my webpage for papers. And also, if you want to work on this or similar topics, then we are hiring. Okay, so that's it.
Okay, well, thank you very much. A couple of remarks about the questions. So the questions are not yet published. So I guess we're going to publish it, like the list of questions, pretty soon, I guess, right? Alexey,
so tomorrow morning.
Tomorrow morning, great. So so I sent around the email address. If you're willing to attack these questions, you can send your solutions to the program committee. We'll share it with Alexey if he's willing to check the solutions, and the official solutions we are going to publish like by the end of the month, I hope, so that you can compare. And we have a Zoom webinar this afternoon. And for all the questions which are left unanswered, you can pose them during the discussion session.
At 3 o'clock.
And there was maybe one quick question. We have 2 minutes. What's the relation between this tool you devised and Lampard's TLA Plus?
Lampard's TLA Plus is a way of specification primarily, right? So it's just a way of formally writing specifications of systems in a particular way. We also have a domain specification language that we cooked up. It's nothing special, it's just a prototype tool, but the strength of the tool is that it can actually automatically and soundly check the correctness of the application or to infer a conflict relation that can make it correct. TLA Plus does come with some tools that are meant for verification. So there's a model checker, but as all model checkers, it doesn't give you a complete guarantee, just a state-based enumeration for some small counterexamples. And there is also a theorem prover, but the theorem prover, you have to invest a lot of effort into doing a manual proof, whereas here we use SMT solvers that are purely automatic. So you can basically specify your application, specify an invariant, and it will go through. So here, the upshot is that here there is more automation.
Okay.
And question, when you share the slides, I'm sorry.
We can put them. I'll send them to Piotr. He can put them.
No, we have your slides. Yeah, we will put them very.
I've done some rearrangements. So anyway, I'll send you the.
Okay.
Okay, thank you.
Okay.
So at 5 o'clock we have the second lecture.
Well, the second course of today is 5 p.m. Moscow time, but at 3:30 we have a discussion with Alexey. So please come with.
At 3:30. At 3. 3.
Oh, 3. Sorry. 3.
At 3.
Yeah. Apologies.
Sure. Yeah. Okay.
In 1 hour.
Okay. Yeah, in 1 hour. Okay. So thank you.
Okay.
Well, thank you very much.
Interesting. Thank you very much. It was very interesting.
Yeah.